Welcome everyone. Thank you for joining us for today's webinar, Arm Endpoint AI Computing Summit 2021. The vast majority of machine learning is running on Arm CPU today. To help developers deploy machine learning on Arm Cortex-M and Cortex-A architectures, Arm has launched the open source CMSIS-NN Library, ARM-NN, and the Arm Compute Library. CMSIS-NN is a set of efficient neural network kernels which aims to maximize performance and minimize the memory footprint of the neural network on Cortex-M and Cortex-A processors. By combining the CMSIS-NN library and the variety of machine learning frameworks, such as TensorFlow Lite Micro, ONNX, and PyTorch, and so on, developers can optimize hardware using ARM processors and micro NPUs to accelerate the deployment of MCUs and NPUs. So today we have invited experts from industry, academia, and ARM ecosystem to participate in the event. We have invited Mr. David Hsu, FAE Director at ARM, who is leading the FAE team in ARM Taiwan to provide solutions required by partners and customers with about 20 years of experience in the semiconductor industry to share ARM's motivation to put together this summit and introduce the speakers. And now I'd like to hand over to David.
Hello, everyone. This is David Hsu. Thank you all for participating in this grand event on Endpoint AI Computing Summit 2021. The term artificial intelligence was proposed in 1956. At that time, due to the limitation of computing power, AI was usually applied to more specific tasks. However, with the advancement of processor architecture and the progress of semiconductor manufacturing process, the current computing power is decent to handle complicated AI, machine learning, and even deep learning algorithms, bring artificial intelligence to people's daily lives, making human life more convenient, safer, and more efficient at work. In the future, the impact of AI on humans will only accelerate and become ubiquitous. I cannot see the end of it. Because of the increasing demand for AI, based on the real-time data processing, security, privacy, and other considerations, AI computing was also spread from the traditional cloud to the edge, and even on the end device. According to Arm's estimation, before 2022, there will be more than 20% of IoT devices with local machine learning capabilities. People hope that each device can be smarter and can do real-time AI processing and calculation while receiving data instead of completely relying on cloud computing. This kind of demand is reasonable, but also full of challenges, like how to balance performance and power consumption, how to put a large number of parameters and models in limited memory, how to make AI models and frameworks easy and faster to deploy in endpoint devices. This challenge requires a joint effort of brands in the industry to overcome. Today's event, I'm honored to invite my colleagues, academics, and Arm ecosystem partners to talk to you about endpoint AI from different angles and share technology, progress, and the results. Our first speaker today is Vice President, Machine Learning Group at Arm. As AI computing is gradually expanding from the cloud to IoT devices, although most of today's machine learning is performed on Arm CPUs, in order to improve the efficiency and the performance of the system, and the dedicated micro NPU is rapidly being adopted, which also brings the visibility for AI machine learning to penetrate into low power consumption endpoint devices. This speech will mention how Arm can reduce development risk, shorten development time, and make products faster by providing trusted micro NPU IP, open source software, and also complete solutions through the collaboration with Arm ecosystem partners. The next speaker we have today is Mr. Hongyi Li, an associate professor at the Department of Electrical Engineering at NTU. I heard that Professor Li is an internet celebrity in the AI industry. In the machine learning course he offered at NTU last semester, more than 1,000 people took the course. There are 4 followers on YouTube and GitHub to follow the teacher to learn the latest technology. Therefore, we are honored to be able to invite Professor Li to share his latest progress in the field of speech recognition. Most of the time, AI learning requires humans to properly label the data. Generally, when training a speech recognition system, it's not only necessary to collect a large amount of voice data, but also to let the machine know the meaning of each voice signal. Otherwise, it will not be able to learn. This learning method is limited to today's AI use range. Take speech recognition as an example. Only language with a large amount of labeled data, such as Chinese and English, can achieve a high recognition rate. However, thousands of languages spoken by fewer people around the world have less labeled corpus, which make it difficult to obtain high-quality speech recognition results. In response to this problem, today, Professor Li will share with you the research results of how to let AI listen, read, and learn on the internet. Using AI self-learning can solve the problem of insufficient manual labeling. Our next speaker is Odin, Principal FA at Arm. He will deeply analyze the current development trend of mainstream smart endpoint devices and how Arm AI solution can be applied to diversified use scenarios. In this speech, in addition to introducing how Arm uses various open source software to develop TinyML to improve software and hardware performance and optimize workload, it will also talk about Cortex-M55 processor and the Ethos-U55 NPU using things like CMSIS-DSP and CMSIS-NN and other commonly used library, simplify the portabilities of the program, let the microprocessors and the micro NPU work closely to accelerate the AI function. Today, Odin will demonstrate the Cortex-M55 processor and Ethos-U55 micro NPU bring unimaginable machine learning performance. Then, we will come to highlights of this summit. We invite all ML ecosystem partners to share with you. First, Google TensorFlow team will introduce the ML framework, TensorFlow Lite Micro. Arm has been working closely with Google on the MCU's machine learning applications. The optimized CMSIS-NN can be used in TensorFlow Lite Micro, which packages complex operations together and can use built-in data processing tools, including TensorBoard, dataset, etc., to help users quickly develop application software on the MCU. In this speech, Mr. Chandler Chang, a senior engineer from Google, will introduce TensorFlow Lite Micro, a representative open source framework to illustrate the advantage of TensorFlow Lite Micro running on bare metal, such as the use of extremely small memory, easy modification, and expansion, etc. Due to the diversity of IoT devices, it's more difficult for developers to select hardware platforms and manage hardware resources for AI application, and they often lack efficiency. We invite Peter Chan, the co-founder of Skymizer, to introduce you the AI compiler, Tiny ONNC, developed based on Arm CMSIS-NN. Tiny ONNC is an easy use but highly efficient compiler. With Tiny ONNC, you can use tools you are familiar with, such as Google Colab, and the data you have to train the model. After the training is complete, deploy the trained model to the IoT device through universal development procedures. In the presentation, Peter will introduce Tiny ONNC and explain why Tiny ONNC assists cloud-native edge AI developed in the development of models. Voice recognition is quite popular in AI applications, such as voice assistant in smart homes, voice control in car entertainment system, etc. Most voice recognition relies on cloud-based service solutions, but it is the same for many products with limited resources. It is expected to have the ability of local voice recognition, but it is not easy for developers to find a solution that can satisfy both recognition performance and cost at the same time. Therefore, we invited Alex Liu, VP of the Embedded Solution BU of Cyberon, to introduce the voice wake-up and the command recognition algorithm dispatcher they developed for endpoint devices. Dispatcher has been successfully ported to the Arm VAM architectural platform. Alex will explain how Arm VAM can meet the computing performance required by dispatcher. He will also further introduce dispatcher's characteristic of high recognition rate, low computing resource consumption, even under noisy conditions. Humans have the ability to understand the world around them through the senses. For example, by hearing abnormal engine noise, you can judge whether there is a problem with the car engine. Or by hearing a call, you can find out if someone is unwell. If you can detect the failure of another machine by monitoring the machine and send alarms to reduce downtime, reduce risk, and solve production problems, improve production efficiency, and improve the human resource required for maintenance. Edge Impulse is an integrated development platform for embedded machine learning on edge device. Thousands of companies and more than 30K projects around the world use this platform. Today, we invite Yang Boom, co-founder and CTO of Edge Impulse, to discuss with you how embedded machine learning can bring smartness and intelligence to Arm-based devices. Today's Arm Endpoint AI Computing Summit 2021 has a very rich agenda, which will last for 5 hours. I believe you are very excited about the upcoming speeches by the AI expert and the ecosystem industrial elite. Vice President, Machine Learning Group at Arm, will share his insights into Arm's visions for machine learning. Please help me welcome our speaker.
Hello, my name is Dennis Luddick, and I'm head of marketing here for the machine learning group here at Arm. AI is a once-in-a-generation change in computing. It's really exciting. It's expanding the capabilities of all devices, from data centers through to the tiniest of IoT devices. The opportunities that AI presents to all of us is massive. Here at Arm, we've been working on AI for many years. We see ourselves as the foundations that our partners need to realize all of the opportunities there are in AI. In this talk, I want to talk a little bit about what Arm is doing to make it easier to innovate, for our partners to innovate, to reduce risks, and to get to market faster with highly innovative AI-enabled products across the board. First off, let me talk a little bit about who Arm is. Many of you may not know, some of you may. Arm is a semiconductor IP provider. We have around 500 silicon partners today. These include household names from the tiniest of IoT devices through to automotive, through to some of the most powerful supercomputers are now powered by Arm technology. Here at Arm, we focus on very energy efficient technology and the software and tools that go with that. And we've been reasonably successful. Arm's partners have shipped to date over 190 billion ARM-enabled ARM-enabled devices out into the market. But one of the things that's really important to Arm is we know that being successful in modern technology isn't about individual companies really anymore. So one of the biggest things behind Arm is we nurture a vast network of partners and ecosystem associates. So we have over 1,000 people who work within our partnership. And they're at the foreground of the forefront of AI in almost every industry. So first off, before we go into AI, how did we get here? And frankly, where in the earth are we going? So AI, or more accurately, machine learning, started in data centers for the most part. And the reason behind that is that's where the data is. So for example, if you want to create a model, a machine learning model that will detect cats, what you need to start with is millions of pictures of annotated pictures of cats. And of course, those are in the data centers. But it's useful to separate machine learning or AI training and inference. Inference, of course, is using the model. Training and inference are very different problems. And from a compute perspective, they need very different solutions and they have very different deployment models. Training, for example, requires massive amounts of storage, compute, and it takes really, really long runtimes in many instances. So historically, cloud and data centers is where people do experimentation and create new neural networks. However, now that we have some stability in the models and the use cases, so in particular, we're seeing a lot of focus and stability around what we refer to as the 3Vs, so voice, video, and vibration. Now that those are stabilizing, machine learning is rapidly moving to the edge, and we've seen this for a number of years. Why? Because that's where the input is. So, for example, once you have a model of a cat, you then want to go and use that model. And where you're going to use it is typically on a device. So you're going to have a camera that's now looking for cats. So you want to deploy that model for inference onto those devices. And the same can be said of almost any other network. So for example, there's a lot of cameras in the world that want to start doing something different once they detect that there's a person in the scene. So adding that ability to detect a person in the scene is really important. Motors, being able to do motor control or vibration sensing, maintenance sensing, local to the device makes the most sense. So we're seeing a rapid explosion in inference in both the edge and the endpoint devices. Why is it moving to the edge? Well, there's a number of different reasons that are driving this. One of the first ones, I mean, we refer to these as the laws of economics, the laws of the land, and the laws of physics. So if you just look at, for example, bandwidth, the number of cameras that are going into the world is just massive. If all of those streams have to be shipped up to the cloud to be processed to do identification of what's in them, to detect whether or not there's a cat in them, that's a massive amount of bandwidth that, quite frankly, the world just can't sustain. So it's just not practical to be able to send all of that information and all of the sensors and all of the other data in its raw format, in its bulky format up to the cloud. It's just not going to happen. And if you could, the processing power, the data centers you'd have to build to be able to process it, again, it's just not sustainable. And that reflects then on the costs. It would be incredibly cost prohibitive to be able to just do everything up into the cloud. And then you have the practicalities of the physics as well. We're all familiar with network connections that are slow, reliability issues. For a lot of these, you can't really have that. They're real-time systems or near real-time systems. You need to have absolute reliability. You need to have very small amounts of latency. And finally, of course, the further you ship something, the more you distribute information, the more it is open to being attacked, the more it's a security risk and a privacy risk. So keeping that device local, particularly when you're thinking of things like personal identification information, healthcare information, these are really, really critical. And so for these reasons, it's important that we keep that more and more of the machine learning is being done on the edge. And we're seeing this happen across a huge number of devices. So if we just look in consumer electronics, this is having a massive impact. So if we just look at consumer electronics, a good example I like to reference is refrigerators. So refrigerators are the second biggest consumer of energy in the average home. It's about 13% of your total energy bill in a household. We have a partner based in Turkey. It's a major appliance manufacturer, a company called Arçelik. And what they did was quite interesting. They implemented a lightweight reinforcement learning algorithm that runs on the device to see if they could improve the performance or improve the efficiency of that refrigerator using machine learning. What it did was it monitored the behavior of the people within the house, and it adapted its algorithms to minimize temperature fluctuations in that particular environment. So it was learning on the fly. And what they found was that with that algorithm alone, just being retrofit, they could produce about a 10% improvement in efficiency. They could reduce the power by about 10%. Now, if you expand that across the entire market, then in Europe alone, we calculate that using this type of technology, you'd be able to shut down 9 power plants, and that's just in Europe. So you can see at a global scale, just looking at Europe and refrigerators, you could imagine what you could get to on a global scale with many devices. Looking across to one of my favorite areas, healthcare. AI is absolutely set to revolutionize healthcare. A simple example is if you look at hearing aids. So one of the challenges behind hearing aids is trying to improve the quality of the audio that people are getting without improving the noise. So you can't simply just amplify everything. That doesn't really help in many cases. So with AI, what you can do is you can actually determine what's valuable audio and what's just noise, and you can help amplify the valuable audio while reducing the noise. And we have partners that are implementing these types of algorithms today. So these are really exciting. These are technologies that are going to improve people's lives. And we're seeing this across the board. Literally every industry is being improved by machine learning. One of the first big areas that we really saw AI take off in devices was in the mobile space. Arm does a lot with smartphone devices. And we saw early days where, in particular around the camera and the imaging pipeline, machine learning was starting to revolutionize things, producing a huge amount of functionality that was really useful. Now we see it across the device. So everything from voice assistants through to predictive text. It's starting to go into all the different functions within the devices. If you go over to infrastructure, so more of the networks that we rely on for our connectivity today, we're seeing machine learning being used for power management of large SoCs with many processor cores. We're seeing it being used for things like 5G beamforming and controlling the data plane. Again, it improves even that. If you go over to the sensor side of things, the tiniest of devices, many sensors are just streams of data. They're producing streams of data. And one of the things that machine learning is really good at is determining what's signal and what's noise. So if you've got any sort of data stream, it's really good at understanding what makes a clean signal in that and what makes noise, and being able to interpret those and separate those. And ultimately, it produces better sensors across the board transparently without people knowing about it. So we're seeing this starting to be everywhere, literally across the entire market. Now, one of the challenges to this, and one of the most interesting things I find from a marketing perspective, is I often get asked the question, what's the most sensible processor for doing machine learning? And I always find this to be an interesting question, because it's something along the lines of what's the best car to use to go on vacation? And the answer is it depends on what you're trying to do. Similar thing with machine learning, running it on devices. We have, of course, neural processor units, which are designed specifically to run machine learning. But I think the mistake that people can make is think that it's just a case of putting down a lot of matrix multiplies. Machine learning is not about that. It's actually a very different problem for different devices. So on a sensor, you don't need to have necessarily a dedicated machine learning processor running. You can simply run those on a Cortex-M type device today. Where you don't need high performance, the latency is not a major issue. Your networks are simple. Those can run on CPUs without any problem today, and many do. In many ways, I think the majority of them probably do. But in other devices where you have a GPU, you want to be able to leverage that technology. And in many devices, increasing number of devices, you want to be able to implement a very efficient machine learning processor. But again, we see a huge range of those type of devices, from MCUs, microcontroller units, through to the big application processors. So from an ARM perspective, what we're trying to do is to make sure that that our partners can implement whatever they need to match their markets. And that goes from the smallest of sensors through to supercomputers and everything in between, from automotive, smartphones, DTVs, IP cameras, etc. So the challenge from an ARM perspective is to build the foundations, which are incredibly flexible, so that people can get the most amount of performance and efficiency from machine learning out of whatever ARM-based device that they are using. So that's really where we're trying to get to. We're trying to get to a point where people can produce specialized processors that are optimized for the needs, no matter what they might be on the different scale of performance area and power. But as I said, it's really easy for people to think that the main thing behind machine learning is just to put down a bunch of matrix multiplies. It's kind of the first thing you go to from a technology perspective, is thinking that matrix multiply is what you need to do. But in reality, from an ARM perspective, it's much more complicated. We invest in a huge amount more than just the matrix multiply, just the hardware. So, for example, from our perspective, we actually invest more engineering time into the software side of things. And so, there's technology within our processors, such as compression and so forth, but we invest a lot in the software, the tools, the ecosystem, the standards that go into trying to make a new technology not only successful, but accessible, risk-free, and safe. So just kind of going down into some of the details a little bit, one of the big areas that we work on is around data. So in many ways, machine learning isn't actually a processing problem. And I think that's something that people quite often get wrong. Yes, there's a processing element, but at its core, machine learning is in many ways a data problem. So there's a lot of focus we put into how to deal with the massive amounts of data that are involved in machine learning, running machine learning algorithms. Some of the approaches that we take, for example, compression. ARM has a long history of doing compression from videos, display processors, graphics, and so forth. And in our processors today, we actually implement a number of very specialized compression algorithms. So, for example, we have different algorithms we use for weights and activations because they're different types of data patterns. And we've got a long pipeline of technologies that we're going to continue to implement, improving the compression. And this has a massive impact on the amount of data and power and performance you can get out of an ARM-based platform. Another example is around what we call intelligent data movement. So, one of the biggest mistakes you can make from a data management perspective is to have to load the same data again and again and again and again. That costs power, that loses performance, and it's just very inefficient. So we put a lot of analysis and understanding into being able to absolutely minimize the amount of data movement we need in running any given network. It's a very complex, specialized area that we spend a lot of time on. And then a third example is around making sure that we understand and optimize around the key operations. So understanding, all the neural networks. We have a massive library of neural networks that we work against, and making sure that we understand what are the basic operations that that need to be created in order to be able to support those in the hardware. Again, an area we spend a huge amount of time. If I then come around to a second area as an example where it's more than just about matrix multiplies, then we look at the models themselves. A lot of the models that are created in the cloud, they were created with a limited amount of care or concern for storage, for memory, for bandwidth, whereas on devices that we have around us, that's something that we have to think about more closely. So one example of how we deal with this is what we refer to as model conditioning. So being able to prune a network, quantize it, deal with sparsity. We found that we can achieve massive improvements in the size and the efficiency of many machine learning networks by going through various model conditioning activities. The second thing is we have performance evaluation tools. So again, we have people's needs in terms of building devices can be quite varied. Similarly, the ways that you can compress and optimize a model can be quite varied. So we have tools which allow people to explore that area and understand what devices and what model optimizations will work really well together to help them achieve their goals. On the more advanced side, we have some early prototyping tools which actually create neural networks. They'll create optimized neural networks from scratch that are optimized for the use case and the hardware that you're planning to target. So it automatically will create networks that are highly optimized for your specific case. And finally, as an example, one of the challenges or big questions that you have in the new technology space is always around whether it's better to have an optimized library or whether it's better to have a native optimized compile flow. Computing history will tell us that compilers tend to win out in terms of optimization, in terms of efficiency, in terms of the ease of being able to access and program something. And so, although we spend a lot of time on libraries today, we also spend a huge amount of investment in compiler technologies to support our different processors. So from Arm, we believe that we have the most complete heterogeneous AI solution available in the market. So as I explained, it's not just about matrix multiplies. It's about being able to provide people with whatever type of processing they need to be able to implement AI in the way that they need to. So from the tiniest of IoT sensors all the way up through automotive, smartphones, up into even data centers and supercomputers. The needs vary quite dramatically. And so we have a huge range of configurable, dynamic, flexible processors, which will allow people to create whatever they need to. But of course, it's not just about hardware. It's one of the biggest challenges is making sure that it's easily accessible. And so we put a lot of investment into the software side of things, ensuring that there's software that will abstract that hardware and try to make it as easy to access as possible, so that no matter what you're implementing, you can still get to that hardware in a consistent way, allowing the software people to have a minimum amount of concern for the hardware and simply being able to target new hardware by simply recompiling. But one of the big things I think that's important for people to realize about our approach is that we're not trying to control everything. We're trying to enable an ecosystem. So when you look up into the framework side of things, we made a very conscious decision not to create yet another framework. There's very effective frameworks. Many people are used to using TensorFlow or PyTorch. And so our approach is to work with those. We upstream a lot of optimizations and technology, and we work with those communities to create the tools and make sure that they can get directly from those tools, which they're used to, down to an Arm, any given Arm hardware platform as seamlessly and risk-free as possible. But of course, at Arm, one of the things that we're very aware of is that it's not just about technology. If you're going to be successful in modern technology today, it's about having an ecosystem. It's about partners. It's about bringing people together to produce complex solutions and enable people to get to market quickly. So we have a large and rapidly growing community of partners in the AI space. And this is just a sample of them from the early parts of the alphabet, and it continues to grow on a day-to-day basis. And we work really closely with these people as the experts in different application areas. Arm can't be experts in everything, and neither can our partners in many cases. So we make sure that we have a really broad network of partners that our partners can work with to be able to achieve a wide range of AI capabilities and take advantage of this massive opportunity that stands before us. So again, all this comes together from my perspective. It's the technology is fantastic, and I love talking about our technology. But the thing that really gets me excited about it is what you can do with it. And from that perspective, AI really is going to change the world. So if we look at just a simple example around electricity. So if you were to look at, I talked about a consumer electronic example earlier on, but if we look over into the industrial side of things, so industrial pumps consume about 10% of the world's electricity. 90% of those are considered to be inefficient. If you were to look at pumps as a country or a nation, they'd actually rank third in terms of electricity consumption worldwide. That's huge. And with 90% of them being efficient, as one of our partners has estimated, there's a huge opportunity to improve that efficiency. And AI is just the kind of tool that's necessary to do that, or that lends itself well to doing that. And our partner has identified that if you were to implement local control to try to optimize the running of those industrial motors, you would probably get a global or an energy reduction of around 15 to 20%. And if you were to expand that globally, that means an energy savings of around 2% globally, which is massive. That's really cool. That's something that's changing the world. And that's what this technology can enable. If you look more around on the sustainability side of things, one of the things that we're really excited about is a partnership we did with the Rainforest Connection. So they're working in Indonesia in the rainforest, and what they do is they take an AI-enabled device, add a solar panel to it and a microphone to it, and they put it up in the trees in the rainforest. And this is sitting there monitoring for audio signals on a 24/7 basis, and it's listening for things like chainsaws, gunshots, motorcycles, or logging trucks. And when it detects one of those sounds, it can then contact a central location, and they can send someone out to investigate and make sure that something bad isn't happening. So that's, again, very cool. So as I've shown, this is a massive opportunity for us. Arm's doing very broad and very deep to try to enable our partnerships. This is exciting. I'm very excited about what we can achieve, and the momentum is really just starting to build. And from our perspective, it's about unlocking opportunities. It's about helping reduce the risks for our partners. And as I said, for me, it's ultimately about helping us all change the world. Thank you very much.
And next, we'd like to invite Mr. Hong-Yi Lee, an associate professor at NTU, to give us a speech entitled AI Learns Human Languages Without Human Teaching.
Hello, everyone. I'm Hong-Yi Lee. This talk is AI Learns Human Language Without Human Teaching. As you know, with the growth of deep learning, the power of AI becomes better and better. However, to make machine learn human language, usually we still need label data. We need supervised learning to teach machine how to solve the tasks related to human languages. Let's take speech recognition as example. To train a speech recognizer, today you not only have to collect a large amount of speech data, you also have to annotate the speech data. You have to tell machine what is the content in those speech signals, or machine cannot learn how to do speech recognition. However, as you know, collecting label data can be very expensive. On the other hand, human baby can learn human language with very little supervision. Can machine have the same ability? In this talk, I will share with you some technique that can make machine learn with little supervision. This talk is AI learns human language without human teaching. To make AI learn human language, we want AI has 4 capabilities. AI can listen and understand what human is talking about. AI have to generate the speech signal that human can understand. AI has to be able to read document. AI have to be able to write the document. Listen, speaking, reading, and writing all together is called human language processing. Human language processing is a very big area. There are a lot of different technology involved in human language processing. Due to time limitation, it is not possible to go through all the technique today. However, we can simplify the technology of human language processing into finding 4 categories of function. Consider that in human language processing, model have to take speech or text as input. Model have to generate speech or text. Enumerate all the possibility. We have 4 types of function we want to find in human language processing. So we might want to find a function which can take speech signal as input and output text data. For example, speech recognition can be considered as a function which takes speech signal as input and output the transcription. For the second type of function, it takes text as input and output speech signal. TTS, text-to-speech, is one example. The third type of function takes speech signal as input and generate another speech signal. For example, denoising. In denoising, your function takes clean speech as input and output noisy speech. For the last type of function, machine take text as input and output text. Question answering can be considered as function 4. So in question answering, your function take question as input and output the answer of the question. Then the problem is how to find those functions. Consider speech recognition, which takes speech signal as input and output the transcription. As you know, speech signal is very sophisticated, so this function should also be very sophisticated too. It would be so sophisticated that we even cannot write down its formulation. If human cannot write down those formulation, how can we find the function? Thanks to deep learning technology, today it is possible to find those very sophisticated functions. To find a function which takes speech signal as input and output the transcription, we have to collect some training data. So this training data will tell AI what is the relationship between the input and output. So to train a function, to find a function which takes speech signal as input and output the transcription, we not only have to collect the audio signal, we also have to provide the transcription, the corresponding text of those speech signals. With those training data, deep learning can find the function automatically. Let me give you another example. For question answering, the input of the function is the query, and the output of the function is the answer. To train this function, you need some training data. So you will tell your machine that when the input is question 1, the correct answer should be answer 1. When the input is question 2, then the correct answer should be answer 2. With this kind of paired data, with this kind of label data, machine can find a function for question answering automatically. We can do that due to deep learning. Deep learning sounds very powerful. However, there's still some problem in deep learning. To train a model to find a function, usually we need a large amount of label data. Only collecting a large amount of speech signal is not sufficient. We also have to label, we also have to annotate those speech signals. This learning scenario is called supervised learning. So when you find your function with the label data, this is called supervised learning. To train a speech recognition system, usually we need more than 100,000 hours of English label data to train an English speech recognition system. However, even though we have more than 100 hours of English label data, with those label data, we can only find a function to transcribe English. There are more than 7,000 different languages in the world, and speech recognition is not the only task in human language processing. However, spend lots of cost, collect lots of label data, we can only solve one task in one language. To solve all the tasks in all the different languages, we have to collect a large amount of label data for them. But it is impossible to achieve that. So how can we solve this problem? Let's consider human beings. Human can learn our language with only very little supervision. You do not need 100 hours of label data to learn a language. Human babies can learn human language with only very little label data. Can AI have the same ability? Below, I will share some technique that can let AI learn with less label data. The first technology I would like to share with you is self-supervised learning. This is the framework of self-supervised learning. In self-supervised learning, the training has two stages. In the first stage, you use a large amount of unlabeled data to pre-train a function. The first stage of training is called pre-training. The function 0 is actually useless. It cannot solve the task you want the machine to solve. Then why we need this function 0? This function 0 can be fine-tuned with a little bit label data, then the machine can find a function you want. Let me give you a concrete example. Let's consider speech recognition. You can collect a large amount of unlabeled audio from the internet. With those unlabeled audio, you can pre-train and obtain function 0. This function 0 cannot recognize speech. It just learns from a large amount of unlabeled data. However, if you want a speech recognition system, you only need very little label data. You provide some label data, and you use those label data to fine-tune the function 0, then machine can learn how to do speech recognition with only little label data. Let me give you another example. Consider that you are going to build a question answering system. It is very expensive to collect lots of label data for question answering. But it is relatively easy to collect a large amount of unlabeled documents on the internet. So you collect large of unlabeled text and use those texts you can pre-train function 0. Function 0 cannot solve question answering problem. But only with a little bit data, you can fine-tune function 0, then function 0 can do question answering. This is the power of self-supervised learning. Among all the self-supervised learning models, the most well-known one is BERT. I believe lots of you have already heard this technology. BERT is actually function 0 here. Let's take a look at how BERT pre-trained from those unlabeled data. So to train the BERT model, first of all, you have a lot of unlabeled data, then you random sample some sentences from your unlabeled document. So there are lots of different sentences in the document, just random sample some of them. Then you mask some of the tokens in the sentences. Then you train your BERT model to predict the mask token. Training the BERT model do not need any label data. You only need some sentences. You only need to mask the sentence, and the BERT has to learn how to predict the masked tokens. Because we know what token is masked actually. So training a BERT model do not need annotation. You do not need to recruit some people to annotate those documents collected from the internet to train BERT. You can directly use those unlabeled data to train the BERT model. The interesting part of the BERT model is it does not only solve one task, it can solve a large amount of different tasks. So with this BERT model, with function 0, BERT is function 0 here actually, you only have to fine-tune function 0 a little bit, with some label data, then it can do question answering. Fine-tune it a little bit by some data for machine translation, then it can learn how to do machine translation. Fine-tune function 0, fine-tune the BERT model with some data of human dialogue, human conversation, then machine can become a chatbot. So this is the power of BERT. With a large amount of data, you can find a function 0 not only solve one task, but many different tasks. Because BERT can solve a large amount of different tasks, today to evaluate a pre-trained model, to evaluate the BERT-like model, you will evaluate across a large amount of different tasks. There's a very well-known benchmark corpus called GLUE, General Language Understanding Evaluation. In GLUE, there are 9 different tasks. To evaluate how good a pre-trained model is, you will use the pre-trained model to solve all the 9 tasks and get the average accuracy. This is called BLUE score. The average accuracy over the 9 different tasks is called BLUE score. And I make a mistake. I say BLUE score, but it's not BLUE score, it's GLUE score. Sorry, BLUE score is another different thing. So probably we restart these pages. So please allow me to restart these pages. So as I have mentioned, BERT can solve a wide range of different tasks. So today, to evaluate how good your BERT model is, you will not only evaluate it on one task, you will use your BERT in a large amount of different tasks. There's a well-known benchmark corpus called General Language Understanding Evaluation. GLUE contains 9 different tasks to evaluate a natural language processing model from all different aspects. And to evaluate how good a BERT-like model is, you will ask the model to solve all the 9 different tasks. And you obtain an accuracy from each task. Then you compute the average, and then you compute the average score, average accuracy of all the different tasks. Then you obtain a score called GLUE score. And GLUE score is widely used to evaluate how good a pre-trained model is. So this is the result on the GLUE benchmark corpus. Here, each column represents one pre-trained model. There are different types of pre-trained models. And each point here represents the performance of the pre-trained model on a specific task. And there are 9 different tasks in the GLUE benchmark corpus. Here, blue curve is the GLUE score, the average over the 9 different tasks. And the black one is human performance. And you can find that with the development of the pre-trained model, probably trained with more and more unlabeled data and with some new technology, the performance of the GLUE score, of machine outperform human performance now. I would like to share with you another amazing achievement of BERT. BERT can not only learn from one language, it can learn from a large amount of different languages. So you can use not only English to train the BERT model, you can use many different languages to train the BERT model. The BERT model trained by different languages is called multilingual BERT. And Google has released a very powerful multilingual BERT, which is learned from 104 different languages. The amazing achievement of multilingual BERT is it can do zero-shot reading comprehension. That is, to teach the multilingual BERT to solve question answering, you only have to provide English label data. If you use English training example to train the multilingual BERT, let it automatically learn how to deal with the question in Chinese. This is a very surprising result. Even though multilingual BERT has never seen the training example of Chinese question answering, with the training example of English, it automatically learns how to solve the question in Chinese. Here is some real numbers. So here, the first row is the result without pre-training and fine-tune on Chinese QA label data, and also testing on Chinese QA label data. The F1 score here is 78. If you do not know what is F1 score here, just consider it as accuracy. The bigger, the better. Then there is BERT. It is pre-trained on Chinese data and fine-tuned on Chinese data. Then you can get 89% F1 score. This is a pretty good number because human only achieve 93% F1 score on the same testing data. So the performance here is already close to human performance. But what I want to emphasize is this result. You use more than 100 different languages to pre-train your model. Then you fine-tune your model with English QA data. Then directly test your model on Chinese QA questions. Then the F1 score is 78. Even though machine never seen Chinese QA training example before, it has never seen Chinese question. With the English QA training example, it automatically learned how to deal with the Chinese reading comprehension task. And it is as good as the model directly trained on Chinese without pre-training. So this is an amazing achievement of multilingual BERT. So in the future, if you want to build the question answer model for all the different languages, you do not have to collect the training data for all the different languages. Collect the data of English is good enough to transfer to different languages. So this is an amazing achievement of multilingual BERT. We have seen the example of BERT. BERT pre-trained on large amount of text data and can solve the task like question answering. But how about speech? Can machine learn from a large amount of unlabeled speech data? It is possible. Today, with a large amount of unlabeled speech, you can collect this kind of data easily from the internet. You can pre-train your function 0, and you can fine-tune the function 0 on the task related to speech processing, including speech recognition, speaker verification, emotion recognition, and so on. Okay, there's a project about self-supervised learning speech model. This project is called SUPERB, Speech Processing Universal Performance Benchmark. The team members are from NTU, CNU, MIT, Johns Hopkins, and Facebook AI. And we already published a paper at the Speech Talk Conference, Interspeech. And because this is a very large project, there are a lot of team members working on this project. Due to time limitation, I cannot go through all the details of this project. For more detail, please refer to our paper published at Interspeech 2021. I would like to briefly introduce SUPERB here. SUPERB can be considered as the decasome of self-supervised model of the pre-trained speech model. There are lots of different pre-trained models learned from a large amount of unlabeled speech data. And probably they have different performance because they learn from different data sets with different technology. And I would like to know, does those models work well on all the different speech-related tasks? So we have SUPERB. It's the decasome of pre-trained speech model. And there are 10 different tasks in this decasome, and there are 10 different tasks in SUPERB. We want to see whether there's a pre-trained model that works well on all the different tasks. And let me introduce the task a little bit. There are some tasks related to content. So we have phoneme recognition, we have keyword spotting. Machine have to classify an audio segment belong to which keyword. We have typical speech recognition. I believe I do not have to describe what is speech recognition. And we have a query by example. Given an audio archive, a spoken query, machine have to identify whether the spoken query exists in spoken archive or not. We have 3 tasks related to speaker. We have speaker identification. We have speaker verification. Given 2 utterance, machine have to determine the 2 utterance belong to the same speaker or not. We have speaker diarization. In speaker diarization, you provide the machine, for example, meeting recording. there are several different speakers in the meeting recording, and the speaker diarization model have to identify some segment belong to speaker A, some belong to B, and in some cases, A, B alter at the same time. There are some tests about semantic. For example, we have intent classification and slot filling. Usually, intent classification and slot filling belong to natural language processing. That is, your model take text as input. But here, the model have to take speech signal as input and directly do intent classification and slot filling. We also have emotion recognition. So machine take an utterance as input. It has to determine the emotion of the speaker. So there are 10 different tests in Superb. And here is some result. We have a big table. I believe you have, it is very difficult to go through all the numbers here. I'm only going to provide the summarization result. So here, each column represents a task. We have different tasks here. And each row represents a model. F-bank here is the result without any pre-training. And here we have the result of several different pre-trained speech models. And we want to know whether there are some of the model achieve good performance, whether there are some of the model is better than other models. Here we first compare the result without and with pre-training. You can find that in most of the cases, for all the different models and all the different tasks, in most cases, pre-training can improve the performance. This shows the power of self-supervised learning. And we further found that some model can outperform the result without pre-training in all the different 10 tasks. So those models are very universal. The self-supervised model, the pre-trained model, the function 0, of those methods, they can solve 10 different tasks. And we also found that Huber and Web2Vec, they outperform other models. And we have a web page for this project, and we have a leaderboard. So if you have any ideas about self-supervised learning, if you train any new self-supervised model, welcome to submit to the leaderboard. So the first part is self-supervised learning. Then I'm going to briefly share with you how generative adversarial network and GAN can use to achieve unsupervised learning. Until now, even with self-supervised learning, we need some paired data, we need some label data to learn speech recognition. Can machine learn without any label data? If we have a large amount of audio and large amount of text, if those speech data and text, they are not aligned, they are unpaired, can we train a speech recognition model in these cases? This sounds very difficult, but it is possible with generative adversarial network or GAN. I believe the speech lab at National Taiwan University is the first lab in the world that developed unsupervised speech recognition technology. In 2018, with GAN, we can achieve 33.6% phone error rate on a benchmark corpus called TIMID. Of course, 60% error rate is a very poor performance. However, it's better than random. This shows that machine can truly learn something from unpaired data. Then lots of different groups further improve the performance of unsupervised speech recognition. For example, Tencent achieved 41% phone error rate on the same benchmark corpus. In the next year, we achieved 33% phone error rate. Some people ask me, does 33% phone error rate good enough? 33% phone error rate is actually pretty poor. You cannot use this system for commercial system. No one will use this system to earn some money. This is useless. However, I can show you the result below. I would like to tell you some history. 30 years before, when the researchers started to use machine learning technique to make the machine learn how to recognize speech, the performance is not good at the beginning. 30 years before, even with the labeled data, but at that time, we do not have deep learning. So the performance of speech recognition system is still very poor. And its performance is also approximately 33% error rate. However, today, after 30 years, speech recognition is already commercialized. You can use lots of online speech recognition systems. So probably, although today unsupervised speech recognition system is still very poor, probably after 30 years, its performance can be as good as today's supervised learning. So I can tell, so when people ask me whether this performance is useful, I will tell you that probably after 30 years with the development of unsupervised learning approach, we can achieve good performance. However, based on some development recently, it looks like we do not have to wait 30 years for unsupervised learning to be as good as supervised learning. Just a few months before, May this year, Facebook announced their result about unsupervised learning. Based on the GAN technology we proposed before and the very powerful pre-trained model we have to back, they achieved amazing results on unsupervised learning. Actually, they achieved 5.9% error rate without any labeled data. The performance is almost as good as a large amount of supervised models. So it looks like learning without any teaching is possible. The third part I would like to share with you is meta-learning. What is meta-learning? Meta-learning, also known as learn-to-learn. In typical machine learning, some developer, a researcher developed the learning algorithm so machine can learn. In meta-learning, the learning algorithm is not developed by human anymore. We use machine to develop the learning algorithm. Machine is smart enough to invent the learning algorithm, and hopefully the algorithm invented by machine can be more efficient than human designed learning algorithm. Let me give you an example about how to use meta-learning. Let's consider speech recognition. Today, we probably have a large amount of data for some high resource languages, for example, English, Mandarin, and so on. And we can not only use those data to train a speech recognition system, we can use those data to learn the learning algorithm for speech recognition. Probably in the future, machine can invent the learning algorithm for speech recognition, and machine can learn speech recognition more efficiently. If this becomes true, in the future, if machine want to learn how to recognize talking, we do not have to collect large amount of data. Because machine has a good learning algorithm, probably only with a very small amount of data, it can automatically learn how to recognize a new language. I know meta-learning sounds very sci-fi. Learn to learn, learning and learning algorithm by machine itself sounds very sci-fi and sounds not realistic. But actually, this research direction has been widely investigated. Here I have a table to list the paper using meta-learning to improve human language processing in the last 3 years. So here, all the rows are different applications. And actually this table is pretty large. I cannot put it in one slide. So this table is pretty long. And you can find that the meta-learning technology have been applied on a wide amount of different tasks. So it looks like meta-learning is a promising direction. To learn more about meta-learning, you can check the link below. I put the paper list I surveyed in this link. Last but not least, what is the next we can do? When we talk about BERT, I already showed you that BERT is a very powerful technology. However, when we talk about BERT, usually the impression is it's a very, very large model. It's a giant. BERT has 340 million of parameters. And actually, BERT is not the largest model today. There are a large amount of models much larger than BERT. For example, in the old time, we have Elmo, it have 94 millions of parameter, and then we have BERT have 340 millions of parameter, and in 4 years before, we think they are already pretty large. But then here comes GPT-2. It is 4 times larger than BERT. However, GPT-2 is nothing today because they are larger models like Megatron and T5. They are 5 times, 10 times much larger than GPT-2. And Turing NLG is even larger. It has 17 billions of parameters. But Turing NLG cannot be considered as a very big model today. GPT-3 is 10 times larger than Turing NLG. GPT-3 has 175 billions of parameters. If we transform the number of parameters into height, and we consider BERT as 1 meter, and actually this is me, then GPT-3 is as large as Taipei 101 behind us. So GPT-3 is much, much larger than BERT. Even though in the past we consider BERT as a giant, GPT-3 is even bigger, much, much bigger than BERT. And even GPT-3 is not the biggest model today. For example, switch transformer have 1.6 T parameter, is 10 times larger than GPT-3. So we have all kinds of powerful but gigantic model in the world. They are powerful, but they are too large. The problem is we cannot deploy those machine learning models in the resource-constrained environment. For example, on drone or smartwatch. On those edge devices, we only have very limited computing resource and very limited storage. Those powerful but giant models cannot be used on those edge devices. So this is why we need tiny NL. We need to make this model smaller. Of course, there are several challenges for tiny NL, include the data set, include the data part, and the optimization of model. In the next talk, Odin will talk about how to deal with those challenges in tiny NL. This is all I want to share with you today. Thank you very much. And if you want to learn more about the advanced deep learning technology or human language processing technology, welcome to visit my YouTube channel. Thank you very much.
Thank you, Professor Lee, for the detailed introduction. And next, please help me to welcome Odin Shen, Principal FAE of Arm, to give us a speech, Unlock the Potential of Endpoint AI with Arm Solutions.
Hi, thanks for joining us. This is Odin, Principal Engineer from Taiwan. Look at the machine learning and the automotive technology solutions. As a developer, AI on the edge is one of the interest topics because all the developer, they want to deploy the more intelligent on the edge device. Today, I will give you the overview of the Arm machine learning technology and the deep dive the latest Arm Endpoint AI solution offering. Also, I will use the two live demo to showcase how to leverage those existing open source software stack and the tooling to build up your idea into the AI endpoint profile. Hope you enjoyed this talk and feel free to let me know if you have any questions. Arm, as a known computing architecture provider, since 1990, the Arm-based chip has been shipping over the 190 billion. Just 2020, the whole year shipping was over 23 billion. More than the 95% of the smartphone are based on Arm. Besides the smartphone, a lot of consumer, IoT, automotive, and also infrastructure applications are running on the Arm technologies. Arm has the larger computational footprint in the world, from the sensor, smartphone, to the supercomputer. As those numbers shows, Arm provides the best computing architecture around the world. Thanks for those of a dramatic improvement from the communication process technology and also computing architectural revolutions. We believe that there will be the 1 trillion ARM-based device in the near and future. One of the main driving force will be the artificial intelligence, AI. Typically, machine learning can be separated into the 2 phases, the training and the inference. Artificial intelligence really kicking off in the hyperscale data center before. As we know, the most important computation problem facing today is to identify the picture. If you want to identify the picture, you need the building of the picture to train the machine learning model. Once of the training has been trained, it's usually to separate the training and the inference because that is a very different deployment requirement. The inference has been happened in where the input data is, the data that you want to process and test when you use the machine learning model. So one of the consensus is the training may well occur in the cloud, but today, that is a lot of inference happens on the edge device. Now, let's focus on the machine learning inference part. In order to make the machine learning work well on the tiny, low-power device, what kind of solution will be? That we investigate a lot of AI use case. It could be vibration abnormal prediction. It could be image object detection. It could be neural language processing or facial recognition. Those also diverse use case has a different input type and based on the different neural network architecture. From performance and the data type point of view, we can also observe the similar diversity. Like ADAS sensor fusion require building together input from multiple lidar, and the camera around your vehicle. That is a total different than the keyword spotting in your smart speaker. AI workload is not restricted to the single computing component, but across the multiple computing engines. One of the common use case is the portrait mode, the key feature of the modern smartphone that allows anyone can capture the professional quality image and the video. This simple feature is computation quite complex. It requires several computing technology execution in real time. In this slide, you can see the multiple stages of the computing pipeline are handled by different specialized AI engines. After we decompose this use case, we observe that the CPU can be used in the pre and the post processing, followed by the GPU or NPU to extract the deep map and the segmentation, passing it back to the CPU, and finally to use the NPU for the superload solutions. Many of the AI workload has a similar behavior like a sensor fusion I mentioned previously. So we talk about the AI demand is diverse, and the inference could be involved in the multiple computing components. And the data movement and the model optimization are two of a critical challenge for the machine learning on the edge. Let's summarize what the industrial need for machine learning on the edge and how Arm can support with that. The first part, the machine learning hardware capabilities. The AI process must be high performance, scalability, and configurability. I will introduce how AI process can fulfill the requirement in the coming slide. The second, the developer also need universal machine learning software developer kit, SDK, which can be applied across all of the computing architecture. As Arm, we provide the open source SDK supporting the most of a common AI framework like a TensorFlow Lite, TensorFlow Lite Micro, Android API, PyTorch, and ONNX across all of the Arm AI process. Today, Deqiang from the TensorFlow Lite, who will give us the introduction how to apply their framework on Cortex-M device in his sessions. Let's talk about the machine learning hardware capability first. To echo the industrial's need, recently Arm announced a total compute solution, which is address those diverse AI requirements. This comprehensive solution integrates powerful AI capability across all of the processor. Arm's total compute strategy based on 3 of the foundation drivers of the performance, security, and the developer access. Based on that, those solutions will provide wide choice to next decade of the innovation across all the device, like smartphone, large screen compute, AR, VR. Here are the few highlights of the massive AI workload, performing gain on the different on IP. Those performance gains vary from the certified average improved on Mali G10 to the massive 7 times on the Cortex-M55 for power constraint use case. Overall, Arm solutions offer the broadest range of AI engine, enable the diverse AI use case like sensor fusion, object detection, speech recognition in different power and cost constraint. In the right corner, here's an example. Partner can build a smartphone SoC architecture based on loads of IP for different AI use case, like image quality enhancement, voice recognition, and the facial recognitions. That is the beautiful of the computing IP component Arm provides, such as the CPU, GPU, and NPU. It allowed our partner to develop the system across the emerging challenge purpose. Different computing problems need different computing components. Use automotive system as an example. Partner will increasingly by combining many of the CPU, GPU, and NPU and their own IP to generate the right computing solution for new autonomous driving systems. We see the same thing going to the server network across the computing spectrum. Now, let's look at how is the universal software stack work. Understand the challenge for the AI developer. They are desire to use the machine learning, vision, and other computing feature to realize their machine learning creativity. We believe that Arm has a unique heterogeneous computing platform to make those of creativity happens on the edge device. The Arm process with the ONNC software, including the framework, inference engine, and the neural net library, which enable the all machine learning use case at the edge across the wide range of the segment and the applications. Underpinning, this is the compute library, which will growing include the deep optimization, low-level feature for all of our IP. The compute library is open source and quality release. Also, CMSIS-NN is another optimized library for most of a common machine learning library targeting for the Cortex-M processor to enable the applications such like the keyword spotting and the image classification. Also, CMSIS-NN is open source and available as well. Alice from Cyberon, who will showcase how to use the CMSIS-NN to develop their deep learning-based voice recognition in his session. Let's dip into the ONNC. ONNC is a set of the open source Linux software and tooling that enable all you need to execute the machine learning workload. This SDK software stack has a fully optimized for Cortex-M, Cortex-A, Mali GPU, and the Ethos NPU. ONNC used a single API integration high-level framework to connect with the computing engine or any of the ONNC backend. Another benefit of the ONNC is quick adoption of the new ARM technology, such like the SVE or SVE2, which we will implement in the latest CPU midnight core. So how the ONNC performance look like? We took 6 different inference software library to a bunch of the real machine learning workload on the big core, little core, and even the Mali GPU. Let's use the Renesmee 9050 as an example. You can see that the ONNC increased 50% of performance in the big core, 60 in the little core, and 3 times improved in the Mali GPU with the other industrial software library. The same of truth on the other neural network model for your reference first. So how do we achieve such of a performance? The key is focus on the critical operations on the real workload. We did highly optimization those critical operations based on each of the computing backend. And most beautiful part is the profiling. We also know that there's many of factors in your system will cause impact the machine learning performance. Could be the CPU utilization, the cache hit rate, system memory bandwidth, and the I/O latency. Streamline provides a single performance view for entire SoC to monitor your application workload from all of the factors. Start from the version 7.4, Streamline has a fully supported ONNC stack, which means that Streamline will automatically profile all of the information I mentioned earlier when you use the ONNC to execute the neural network model. Exciting? Let me give you a quick demo to show how it's works.
Okay, let's quick walk through about the ONNC repository. In this repository, they will include the source code and the related document. In the source folder, we have implemented different converter. In the sample folder, we implemented 3 of the classical neural network example for developer reference, like object detection. As I mentioned in my slide, every 3 months, ONNC will release the latest version in the GitHub. Besides the GitHub, I also recommend to access this web page to understand the whole of the development flow. Because a lot of software package dependency, I will recommend to use another repository. Here is the ML tool solutions. You can find the build ONNC folder. They will include automatic download, setting, and the compiler script. This script will build out the software depends on your developer involvement. The goal of today's demo is use the Streamline to analyze the ONNC system performance. So when we're doing the ONNC setting, please make sure the profile backend Streamline must be set. Therefore, the Streamline can completely analyze the ONNC behavior. After confirm the setting, let's start building ONNC. At the same time, let's look at what is the demo we will run today. Today, let's use a classical example from the same repository, MNext. It's a handwrite recognized model. We will use this model to demo how to use the Streamline. The network architecture is very simple, 28 by 28 input and 10 output. Let's look at the source code. In the source code, you must include the header file and the reference ONNC document to use lots of API. To import the MSNet, you must follow the API here. To use the Streamline to do the profiling, make sure those 2 options must be set as 1. Double check your ONNC folder has been located correctly. Then you can start the compiler. Today's demo is using N1 SDP It is the newest N1 CPU. It's based in the V8.2 CPU architecture, 2 of the core cluster. After execute the demo, you can collect the Streamline log like this one. I'm using the version 7.7. Streamline provide a lot of information for your reference. In this case, the CPU 3 is running in the beginning, then move to the CPU 1. Then all the CPU is run together. Besides CPU, we can also calculate the instruction behavior. In this case, the floating point and the sending instruction on each of the CPU. Based on the Streamline, we can observe a lot of the sending instruction is running during this period. To close reference with the software stack, we can see that this moment they are running our demo example. According to the message you got so far, the CPU loading must come from the ONNC. Streamline has been identified the whole of the ONNC execution period. Also, it is easier to observe most of the computing time has been consumed by the convolution layer. Check the neural network model again. The convolution layer actually the most of a computer hungry layer. Use Streamline, it will be very easier to identify where is your critical bottleneck. You should pay attention to optimize. Let me use another example to explain more. In this case, the ONNC has been set without use the sending instruction. You can see the whole execution time is taking longer and the sending instruction count is keeping low. That is over 70% of the computing consumed by one of the convolution layer. That is a Streamline can easier to identify.
Hope you liked the demo. Here's a several useful links I would like to point to you. Please click lots of links to find more detail. After talking about the generic machine learning solutions, now let's focus on the TinyML segment. One of the definitions of the TinyML is under 1 millivolt active power when the device doing the machine learning inference. Here are several examples, like object detection on the drone, like abnormal vibration prediction on the sensor, and smart speaker keyword spotting. There are thousands of the developers are using like the ST Micro, Arduino, Raspberry Pi Pico, the Numerton developer to create a lot of interesting machine learning use case. If you're interested in more, please don't miss the presentation from the Edge Impulse. They are one of the leading machine learning on edge device development platform provider. They will give you the detail how to create a deployed machine learning application into Cortex-M in later session. As I mentioned, we recommend the developer to use the Cortex-M CMSIS-NN Library. That's because this is a collection of the efficient neural network kernel developer to maximize the performance and minimize the memory footprint on all of the Cortex-M processors. Use real TinyML TensorFlow Lite runtime workload as an example. CMSIS-NN kernel provide more than 4.6 times performance and 5 times energy efficiency compared with the non-CMSIS-NN kernel. Click this link to find more detail. So using the CMSIS-NN framework, developer can easier to deploy the neural network model for all of the Cortex-M processors. As I mentioned, AI demand is diverse. Only apply the standardized software stack may not fit all of the TinyML requirement. When the developer consider to deploy the more complexity neural network model with the resource constrained device, what the challenge will be. So typically, the memory capacity of the MCU device was less than 1 megabyte SRAM and flash. That could be the issue to store the traditional convolution neural network model inside. For the model execution part, this is usually to take a lot of memory footprint for hidden layer processing, which the MCU device cannot avoid. Both of a memory capacity issue are the main challenge for the TinyML. Also, the computing power is another critical issue for the TinyML device. Most of the TinyML device only provide 1 MB operation per cycle, which is way behind the developer need. That is the reason Arm provide Endpoint AI product line. The target application of the Arm Endpoint AI must be the 3 type of typical input data type. They call the 3V: voice, vision, and the vibrations. Based on the old TinyML challenge I mentioned before, we have identified the 5 kind of the key factor to make the TinyML success. The first thing, the computing. We must have the suitable machine learning capability to achieve the real-time workload computing requirement. The second, for specialize the workload and the application, they need different kind of a pre-processing before the neural network model execution. Let's use the smart speaker voice assessment as an example. The raw audio data must be processed by beamforming and the noise cancellation algorithm before the keyword spotting neural network model. For those of a non-neural network-based workload, the suitable endpoint AI solution must be provide the option to along with the CPU to improve the pre-processing performance. The third one, security and the safety. The endpoint AI must be implement root of trust like a trust zone, and also could be certified by industrial standard like PSA. To respond to the industrial need, last year, Arm announced the significant Cortex-M55 processor. Cortex-M55 is the latest Cortex-M processor that is V8.1 Helium architecture, which include MVE vector extension and the SIMD instruction set. They include 8-bit MAC operation per cycle, which is a significant improved convolution operations. TVN, the tiny coupled memory, instruction and the data cache, and the ASI interface enhance the MCU memory throughput compared with the previously Cortex-M product. Also, Cortex-M provide the trust zone technology and the related software package for further TinyML security and the safety request. Let's look at the Cortex-M55 performance deeply. In this graph, the x-axis means the machine learning performance, and the y-axis is the control code single thread performance. You can see that the previously the M4, M35, M7 has a linear performance improve. For the single thread performance point of view, Cortex-M55 provide 5 times of a single processing performance in INT32 data type, supercharging the machine learning performance by up to the 50 times over the previously Cortex-M series. Use the object detection as an example. The Cortex-M55 has increased 5 times of inference speed compared with the Cortex-M7 at the same condition. That means that when the image neural network model consumed 5 seconds in Cortex-M7 platform, the execution time will be reduced to the 1 second in Cortex-M55. Today, many of the machine learning is performed on ARM CPUs. For example, the people need to choose the Cortex-M platform with the Linux operation to excuse the neural network model like object detection application. Due to the cost, energy, and the mobility reasons, developer is looking for the battery power SRAM-based real-time operation system platform, which is able to perform the similar machine learning computing. Also, the marketing trends tell us there's many of the machine learning computing demand on the endpoint AI. That is why we create a new neural network process product line, Ethos-U. The dedicated neural network process, NPU, are becomes more popular because they can dramatically improve the efficiency and the performance of the system. The first two micro NPU, Ethos-U55 and the 65, has been released. The several partners has been announced they are using on their coming product. One of the key value of the Ethos-U process is a wide range of the neural network model supported. Ethos-U55 completely executes the more popular neural network model end-to-end, like image-related, RedNet, MobileNet, extension, and the voice-related DSCNN, deep speech, web-to-later. All of the optimized models are available on GitHub for download, and Arm will continue to optimize the model neural network at upstream. Let's look again the Ethos-U55 performance. To compare with the previous Cortex-M55 only, this IP combination is gained 32 times machine learning performance compared with the Cortex-M55 only device. Took the previously object detection as an example. The inference rate could be 30 frames per second at the same condition. That is the same level of the Cortex-A performance. Let's deep compare with the performance on different IP combinations. Compares previously higher the Cortex-M process core, Cortex-M7, and the two of the Endpoint AI core. Let me use another type of AI workload to compare with the performance. You can see that the 6 times the voice assessment inference improved from the Cortex-M7 to Cortex-M55, over the 50 times improved with the additional Cortex-U55. The energy efficiency point of view, you can also see the significant gain as well. We know every neural network model has a different behavior, and the number we show here is not equal the machine learning model you developing now. In coming slide, I will give you a quick introduction how to estimate your neural network model performance on Cortex-M and the Ethos-U. We believe that is the best-in-class industrial solution for the endpoint AI. Both IP are configurable and scalable to address all of the IoT diversity. The configuration of the Ethos-U55 is quite simple. Partner can set up as the 32 meg to the 256 meg per cycle based on their AI use case. One thing I would like to highlight here, please note that Cortex-M55 can work alone, and Ethos-U55 can also pair with the other Cortex-M processor. After the huge success of the Ethos-U55, recently Arm announced the new Ethos-U65, which is the next generation's micro NPU. There are two of the different. One, Ethos-U65 provide up to the 512 meg per cycle, and the U55 only half of that. Ethos-U65 provide a larger memory bandwidth than Ethos-U55, which can perform more memory-hungry neural network model workload. On the typically SoC architecture, that would be the right-hand side. Ethos-U65 along with the Cortex-M as a standalone system. Also, Cortex-M plus the Ethos-U55, the combination could be the subsystem inside the low power or security domain in the whole of the Cortex-A SoC system. For example, the application domain Cortex-A could be idle and the low power domain calculate as always on same thing. Once the event has been recognized by the Ethos-U55, the application domain will resume from the idle. Here is a performance comparison. You can see that all of the Ethos-U65 performance improve over the 2 times in all of the cases. That means the outstanding micro MPU architecture can gain over the double performance by double the mega capability. After explaining the AI endpoint hardware spec, it's time to talk about how the software developer work. Here's a typical developer flow for the Cortex-M with the TensorFlow Lite. On the host platform, developer needs quantization the tool and convert the training the model into INT8, then executes on the Cortex-M device with the TensorFlow Lite runtime. Here's just a high-level concept of the Cortex-M software flow. In Deqiang's session, he will walk through the more detail how to apply their framework on Cortex-M device. Then, what will be happen when you need to deploy the neural network model, include Ethos-U processor? It's similar. Basically, developer will reuse the same software stack, just added one of a procedure on the host side. The only thing you need to do is the neural network optimizer after the quantization phase. The neural network optimizer identified the graph to run on the Ethos-U and did the optimization, schedule, or location loss of a graph. After the neural network optimizer processed the original graph, the neural network model will be converted into the new customer graph, the more Ethos-U friendly operation string. On the device part, developer just need to make sure the Ethos-U driver has been included into the firmware stack. All other software procedure will be kept the same. Not only provide the best-in-class industrial endpoint AI processor and the software stack, Arm has been pre-integrated system IP, security IP, software stack, and the development tool as the Costone 300. The reference system has been including all the features which the AI endpoint device need. They will benefit our silicon partner to speed up their development cycle and minimize the additional hardware and the software integration effort. For all of the ecosystem partner like the algorithm provider, they will use the Costone 300 as a software reference platform, which can early deploy their algorithm even hardware chip is not ready yet. That's as a Cyberon and many of the software partners are doing now. There are 2 of the options for all of the developer. They can early deploy the Costone 300 reference system. First, the FPGA prototyping board in your left-hand side, the MPS3 board provide the equivalent hardware block for you to apply the software on that. Second, the more efficient way is on ecosystem FVP, the fixed virtual platform. Based on the Arm face model technology, we integrate both the Cortex-M55 and the Ethos-U55 process into the virtual platform environment. That means that developer can install the function equivalent simulator in your host machine instead of the real hardware. I know that would be a little bit abstract. Let me use the smart live demo to walk through the best developer journey.
Arm is continuing to optimize the neural network model. In this repository, you will see we will optimize all models in our CPU, GPU, and also NPU. For this image classification example, we have already quantization as the INT8 format with Apache 2.0, fully optimized on CPU, GPU, and NPU platform. Beside the quantization model, we also provide the recreate folder for the recreate or re-benchmark the model itself. Also, we provide the speech recognition type of a neural network model with the quantization and the pruning version with Apache 2.0 license, fully optimized by CPU, GPU, and NPU as well. Arm will continue to optimize those of model and put in the GitHub for all of the developer use. Now, let me introduce the ML Embedded Evaluation Kit. It's an open source project which can run it on the MP3 and the FVP. I have mentioned that. It comes with the Cortex-M55 and the Ethos-U55. Those models could be running on the evaluation kit. This evaluation kit is the Coston 300 software reference platform. Follow the instruction, you are able to build out the whole related software. As I say, the project is open source. Everyone can download and build by your own. If you want to build everything from source by your own, please follow the page. They will guide you how to do that. You can build that by different hardware, by different configurations. Here is showed all of the dependent package you need to install in your project. Like ONNC, they also have the automated script you can use for install of the related package. Now, I would like to talk to the critical software, Vela, which can fully optimize the neural network on Ethos-U55 before inference. Lots of optimization were based in U55 configuration and the memory size. For example, you can set up the 32 meg up to the 256 meg, also the U65, and the different memory and the different system configurations. Finally, Vela will generate another TensorFlow Lite file. Follow the instruction. I'm sure you have already built out your application. Now it's time. Let's execute on FVP. Now, let's execute the FVP with the binary file we just built out. There were two of the windows will pop out. One is the terminal. Another one is the virtual platform. Let's give it an image and see that it can be recognized as a tiger. Seeing the simulation will take a couple minutes. Let me bring you to walk through the code base. You will see two of the folders, one for GNU GCC, another one for Arm compiler. All of the binary will be stored in those folders. Let's look at the source code folder. You will see the three of the different folders. They will HAL, they will application, and the TensorFlow Lite for microcontroller. The main folder is the application we are running on. Let's look at resource download folder. You will see that there's two of the TensorFlow file inside. The one is the original TensorFlow, another one was compiled by the Vela. This document analyzes the total execution performance after the Vela compiler to optimize the model. They will give you a cycle count and the inference rate. Okay, let's go back to the TensorFlow files. The original TensorFlow file will look like this. The input is 224 by 224 by 3, and the massing of the hidden layer. Then let's look at the TensorFlow Lite after the Vela compiler. The input is the same, but the hidden layer just one. That means the original model has been converted into the U55 friendly graph. The network can execute more efficiency and list about memory access. Now you can see the tiger has been recognized and the related execution cycle here.
Hope this demo gives you an idea how to apply the machine learning model into the Arm Endpoint AI platform. As a developer, I'm sure you want to know when the Cortex-M55 and the Ethos-U55 platform will into the market. Alfie, the supplier of the MCU, recently they announced they will launch the new product family with the Cortex-M55 and the Ethos-U55. NXP, the lead partner of the Ethos-U55, they announced they will upcoming the next generation IDAMX application processor will integrate the Ethos-U65 across the entire series to accelerate the machine learning applications. The HiMax is leveraging the Arm Cortex-M55 and the Ethos-U55 to maximize the edge AI performance with the single tool chain from Arm to significantly speed up the ultra-low power smart camera applications. Those are just a public information for your reference first. More of a product will come into the market shortly. In this session, we start from what the industry need, then introduce the several solutions which has helped all of the partner success into the AI wave. But one of the beautiful paths to success is you, the developer and the ecosystem partner. We know all of you will be the foundation to the success. As always, Arm will continue to engage with all of the AI ecosystem partners around the world. Our partner programs is expanding all the time, and we are seeing the ecosystem align across the common platform. Currently, we have a lot of companies that decide to join the AI partner programs. For your reference, when we start promote the program in Taiwan, we have 4 of the pilot partners join in the past 3 months, and more of the partners is coming soon. They will use this platform to contribute to what they've done with Arm. Here's an example how we bring the ecosystem partner into the Arm platform. Every 2 weeks, our ecosystem team, they will host a live virtual tech talk to broadcast with all of the machine learning developer audience. The content will be all available on the Arm developer YouTube channel for replay. Recently, Mario Bengi, the co-founder from the Arduino, they gave a talk about how to create a tiny emerald project with the Arduino. Please visit our website to find more detail. AI is a generation change in computing that is to change everything from the cloud server to the tiny IoT device. The shift can unlock the creative of the value. It makes existing application better, faster, cheaper, and easier to use. They will make all of the possible to achieve in the small and the low power device. And they will also enable the whole new use case. The opportunities are massive and the market is open to everyone. At the same time, Arm is reducing the risk by providing the Endpoint AI building block and deliver the open source software stack and the tooling to make it easier to unlock the value in those of opportunities. Together, we can solve the problem and catch out the coming big wave. I hope you enjoy this session, and please feel free to reach out to me if any question or feedback. Thank you.
Thank you, Aldin, for your speech and demonstration. And next, please welcome Mr. Dechang Chen, the Senior Engineer of Google. He's going to present getting started with TensorFlow Lite Micro and CMSIS-NN for ML applications.
Hello, everyone. Thank you for attending this presentation. My name is De Chang. I am a software engineer from Google. In this presentation, I would like to share with you TFLite Micro, a library build machine learning applications on microcontrollers. TFLite Micro is built with microcontrollers' tiny memory requirement in mind, and it's portable, extendable. It also comes with hardware-specific optimizations, such as a CMSIS library. We believe TFLite Micro can help build machine learning applications on microcontroller in a more fast, efficient way. So thank you for coming to this presentation, and we'd like to have a more discussion with you and share more with you. This slide is a joint work with my colleagues Tiezhen Wang and Pete Warden. The whole TFLite Micro work is available on GitHub, and we have a small team all available on the GitHub to answer your questions. All right, let's get started. Well, why do we even want to do computation on tiny environment? To start with, let's look at the history of machine learning computation environment. Machine learning applications traditionally start with running computation on powerful server farms with general purpose CPU and GPU. Those CPU and CPU are connected to power strip, so they have unlimited power supply, if you would like to look at it that way. Also, its memory is in the unit of gigabytes, usually. In the past few years, we have seen some trend of loading those computations to the edge side. For example, TFLite hardware accelerator, some of the computations are offloaded to there. Another important edge computing device that we are seeing machine learning computation happen is on the mobile environment. Now, mobile is not connected to power strip, but today's mobile has pretty powerful CPU and also large enough battery that some machine learning computation can happen in mobile. Today, we are going to focus on a different type of environment, which is what we call as tiny microcontroller, MCU, and DSPs. Some typical examples of this type of computation environment are Arm Cortex-M3, M4, and the latest M55 with Ethos-U55 accelerator. What's the advantage of running those machine learning application on this tiny MCU and DSP environment? Well, there are great potentials of combining machine learning technology with microcontroller. Why? Because MCUs are widely available. There are billions of microcontrollers available in the world. In billions, it's just a year's shipment. And if you consider every single microcontroller that has ever shipped and active, the number is only going to go up. And because they are widely available and they are widely deployed, so they get to access more data. And if your computation can happen locally, you also have much less privacy concern because the raw data are not being sent to the server farm. So that's one of the advantages. Another advantage of MCU is they are typically low power, and therefore they have long life, even with just running on a cell battery, for example. That means they can be deployed in environment that has not been considered before. And we will see some examples later on. Now, the advantage of low power also means that these microcontrollers typically cannot be connected to the internet all the time. And they also come with a smaller memory area. So those are the kind of the challenge facing building machine learning application on microcontrollers. Now, a few examples of such application or such potential of combining machine learning and MCUs are always-on voice detection. One of such typical example is on a phone. You don't always run your voice detection all the time. You have a small MCU running the always-on voice detection. And then once you detect the command words, you start the whole voice command interface. There are also applications such as person detection, like it's people around you, it's a particular person in this room, that kind of application. Application that's emerging on, it's like music detection. Basically, it's a small device that can tell you what kind of music is playing around you, or is it the same music that you're listening? Another like toy, for example, in a toy or gadget type of application, it's this Adidas Jaguar Text. It's basically a small shoes insole that you put inside your sports shoes, and it can help measure how long you have been running, how fast you are running, and how fast did you kick the ball. That's just an example using machine learning plus microcontroller on the toy or gadget setup. Needless to say, IoT is also another important area. Honestly speaking, those applications are just emerging, and a lot of potentials could be unveiled if we unblock building machine learning application on microcontrollers. In some sense, if we enable developers to write more applications, we will see more and more applications, and we are able to better come up with different application scenario. So why do we think that there are advanced challenges of building microcontrollers? Well, because it's not actually as straightforward as you building a machine learning application and deploy on a server farm, or even, for example, let's look at how you would build a machine learning application on microcontroller. Like almost all machine learning application, it comes with a new idea. So you go through, you construct your basic model, you go through the training and validating and testing set. And then once you are happy, you have a model. Now the problem is how to run this model on MCU. Unlike a traditional server farm in which you can pretty much deploy such a model, there are a lot of frameworks out there. At the very least, you will be able to directly run such a machine learning model. MCU environment typically does not support a script running. There are some that support that, but it's not widely available and they are more costly. So you go to have experts that understand machine learning model structure and kind of convert that in from the scripting language that represent model structure into something that's runnable on MCU environment. That including understand that language. That also including understand the model such you know certain constructs in a model needs to be removed because it's not useful to keep those constructs on MCU environment, which is purely running inference, for example. Another thing that you need to consider when you're running on the MCU environment is to quantize the weight, because most MCUs, even though if they support floating point, they are more efficient if you run the fixed point. So the weight and other parameters needs to be quantized. So that's another task. And lastly, in order to run that efficiently for specific hardware, you need to optimize it based on the instruction set for that particular MCU, or you need to optimize for its memory constraint, for example. All this together all this together becomes hurdles to build machine learning application fast for MCU environment. And it's basically a lot of work that can be tough to scale up. What we are proposing is that and what we introduce in this presentation is TFLite Micro. And before I jump to that, and let me give you an example why certain expertise is needed for building machine learning application on MCU. On the right-hand side of the slide, you can see a graph structure. This graph structure is actually just doing the batch normalization for during the training. And after training is done, you no longer need this batch normalization. All you need is just actually a constant. However, if you are somebody that's new, you're coming from MCU background and you're new to machine learning model, you may not realize this is actually just something that you can convert it into something that's more friendly to MCU. That's just one example of batch normalizations representation. And there are many different such representations in a model, depending on different frameworks, different algorithms. So you can see you really need to have a lot of modeling in order to take a model and convert it into something the microcontroller can run. Having outlined the challenges and giving examples of challenges that we face of building machine learning application on microcontroller, let's look at what TFLite Micro can do for you. TFLite Micro, as its name stands for TensorFlow Lite for microcontrollers, it's basically a TensorFlow Lite, which is a software framework built for mobile. So you can consider TFLite Micro as a variant of TensorFlow Lite, but built for microcontrollers with much less memory and special ways to optimize for memory for MCU environment. Now, the right-hand side shows how you would build a machine learning application if you are using TFLite Micro. Fundamentally, after you go through similar process of building machine learning model, then you call the tool provided from TFLite and convert it to a TFLite model. Then TFLite Micro will be able to take the model, and moreover, it will be able to combine the model with optimized MCU kernels supplied from different partners, such as Arm CMSIS. And TFLite Micro essentially just becomes a library that can execute machine learning model, and it can be easily combined with your applications. So as you can see, now we kind of abstract the problem into two parts. One is building a model, and another is kind of optimize the kernel. Each work can kind of work independently. So we believe TFLite Micro is a more scalable alternative to build machine learning applications for MCU. TFLite Micro already support a lot of different hardware architectures. For example, Arm Cortex-M3, M4, and M55 with Ethos are all native supported. TFLite Micro also supports MCU from Cadence, as well as DSPs from Qualcomm. It's designed to be easy to port to different platforms. By different platform, we mean like even with the same family of MC and DSP, there are different hardware platforms using that, and they sometimes come with different build environment or compilation environment. Some of those examples could be Adreno, SparkFun, Edge, Bluepier, Cornerstone 300, to give a few examples. TFLite Micro gives examples and instructions on how you can generally project for make build system, for mbed build system, for keys build system. Furthermore, TFLite Micro also come with device-specific hardware optimizations. There are many different optimized kernels that are available from partners. The so-called kernels are basically you can consider it as a mathematical library that's specially optimized for different hardware architecture. There are, to give a few examples, there are already a lot of contributions from Arm. They provide CMSIS optimized kernels. Also, they provide the Ethos custom op as a way to run the Ethos NPU accelerator. One of the advantages of TFLite Micro is that it's built for tiny memory footprint. That's one of the big difference between it and the larger framework like TFLite. To give you samples, TFLite Micro itself is kind of 16 kilobytes at runtime. If you just include some of the operators, it's like 22 kilobytes are enough for running a speech model. Speaking on the model is represented by a very efficient flat buffer. For example, speech recognition, basically a speech recognition model that can recognize simple yes and no command is only like 20 kilobytes. A more complicated vision-based person detection could come with 250 kilobytes. And a motion-based gesture recognition, such a magic one, is like 20 kilobytes only. Now, even at 250 kilobytes, you can see that we're talking like a model size of kilobytes and code size of kilobytes. And if we are not talking a megabyte, so that's a big advantage because a lot of MCU environment has very tight memory constraints. One of the advantages of TFLite Micro is also the size is scalable with number of ops. We provide API for application developer to register only operators they want to use and prune out the unnecessary operator kernels. So basically the larger the model is, the more complicated the model is, the size of the library will increase. But if your model is simple, then the size is small. Another point is that TFLite Micro is built with bare metal environment in mind. What it means is that it's a core library at its core, and there are no OS dependencies. And the TFLite Micro is portable using pure C++ with no standard libraries that use dynamic memory allocation. So it's easy to expand and extend as well. A couple of examples like that we provided in TFLite Micro is like this micro speech example. It basically runs on Adreno Nano circuitry with Arm Cortex-M4, and it can recognize simple yes and no. In the example, we also provide the training script and data. This is kind of running a very small model example. On the other end of the spectrum, it's running vision applications. This is detecting whether a person is in the room or not. So the model is the application capture 96 by 96 image and provide it to the TFLite Micro to run a vision classification. Again, as usual, we provide training script in the example. Now, these two applications are the two spectrums of the application. One smaller with audio and speech, the other is a vision. Hopefully, it gives you a basic idea of what TFLite Micro is capable of. Now, let's talk about how you can get started with a TFLite Micro. TFLite Micro is an open source code. So it's available and downloadable from GitHub. It's on GitHub. You can also file GitHub issue. To start with, we recommend you always start with a hello world. It shows you how you can train a model to how you can integrate with applications. So you can use it as a project template. We also provide many instructions on how to run hello world in different hardware platforms. So it's a very good starting point. Now, instead of going through the hello world example step by step, instead, what I would like to talk about is a few key concepts and key steps in TFLite Micro to help you getting started. To start with, we have mentioned that it's not easy to export a machine learning model to MCU environment. Now, would it be easier with TFLite Micro? And the answer is yes, and it's deceptively simple. On the right-hand side, you can see the code snippet. Basically, what you do is just create a converter. This comes with TFLite toolset. And then you configure the quantization parameter. Then you just convert it. And because MCU environment typically don't provide file system, so you probably just want to use the XSD to convert that model into a binary block. And TFLite Micro would take that binary block and run it through the system. This quantization is deceptively simple, but under the hood, it does a lot of stuff. And converting flows, removing the backward pass, removing the training-only construct, converting with variable from variable to constants, and sorting graph into a execution order. Now let's look at the TFLite Micro internal. The key concept or the key entity inside TFLite Micro is this entity called interpreter. It accepts the TFLite model in flat buffer and convert it to a graph. And a graph is basically a graph of nodes, and each node being an operator. An operator is a description of what kind of operation it's run. And like, for example, convolution, full connected, addition, and so on and so forth. Interpreter would take this graph of ops and execute this graph sequentially by calling each ops function. Now, before we can execute this graph, another thing that an interpreter needs to do is do the memory allocation. Remember that we say that we do not support dynamic, we do not want to support dynamic memory allocation. So we provide a memory allocator that can allocate any space that the graph or the model wants. Essentially, the application will provide a fixed size arena, and interpreter and through the memory allocator would reserve the buffer inside this memory arena, and we will try to optimize it by respecting the buffer's lifetime. Needless to say, an error will be returned if arena is too small. Now, once we have a graph operator and if we have a memory allocated, interpreter will run this graph through the operator. Each operator is implemented by a kernel. There are different types of kernels. There's this reference kernel, which is a standard readable code, but it's slow. The other is a platform provide optimal implementation, such as Arm CMSIS that I have mentioned. Cadence and Qualcomm also provide some of the optimized kernels. And user can register op that they want to use instead of supporting all the ops to save the memory. Now, so far, I have been talking about actually built-in op, which is the standard operator that a model provides, like, for example, convolution, addition. But there are cases in which that you might want to add your own operators. And that's supported by something called customer op. Customer op, like its name suggested, it expands support to unsupported operator. One of the key usage that has been used by Arm as well is that it's used to support hardware accelerator. An outstanding example is the Arm Ethos NPU. This comes with the TFLite Micro code. And in this slide, we provide a link to that example code, as well as a link to the outstanding presentation from Arm folks about how they integrate the Ethos with the TFLite Micro. So please go and read that presentation. It's really good and really informative. To conclude, hopefully we have convinced you that there are a lot of potentials of building machine learning applications and run it on MCU and DSPs. TFLite Micro is kind of library that built to run machine learning models in memory constrained environment such as MCU and DSPs. It comes with platform-specific optimization such as CMSIS from Arm to help you speed up the building efficient machine learning applications for embedded systems. We hope that you pick TFLite Micro as your choice to build machine learning application on embedded system, and your contribution to this open source project is greatly appreciated. Thank you very much.
Thank you, Deqiang, for your sharing. Welcome to our next speaker, Peter Zhang, the co-founder of Skymizer, to talk about Tiny ONNC, driven by CMSIS-NN, unleash the intelligent power of your IoT devices.
Hi, everyone. I'm Peter Zhang, the co-founder of Skymizer. I'm going to introduce Tiny ONNC, a CMSIS-NN-based AI compiler, unleash an IoT device intelligence power. AI has shown its advantage in many fields on server-class devices from 2012. But how about AI in IoT devices? IoT devices face many harsh environments, so they only provide a limited hardware resource, especially in memory. Like one of the most powerful devices provided by Arm Cortex-M is NXPRT1050, which has Cortex-M7 600 megahertz CPU, 512 kilobyte RAM. But in most cases, like in Australia, wide field, like in a baseball field, it's very limited environment. You cannot use this powerful device. So you only can use like Cortex-M4 series, which is a very succinct, very tiny device, which has 100 megahertz CPU with 128 kilobyte RAM and 512 kilobyte flash. And even more, in some cases, you only have 64 kilobyte RAM and 64 megahertz CPU. So unlike server, you only have very, very limited RAM and flash. What does this mean? It means putting AI model into this limited memory may lead to AI models computing power also decrease. Like when you put in an AI model with 500 kilobytes, you may have 80 million operations. You can easily put this model into Cortex-M7 device. But when you choosing Cortex-M4 device, you only have limited memory. So you only have like 64 kilobyte memory. So you cannot put 80 million operations. You only can put 6 million operations. And what does this mean? It leads to the limited computing power. Also leads to you have to sacrifice your accuracy, like you may sacrifice 5, even 10% accuracy. For some scenario, this is unbearable. You cannot put this low accuracy device in your field, in your application. So most of AI solution integration, system integrator, the most cost, the most time they spend is software instead of training. This software means they spend lots of time on porting AI model to various IoT devices. They need to try to trade off between accuracy and the code size, the performance, and even the cost of the layer boards. So we're thinking, is it possible for us to create an AI compiler to optimize the memory usage, but without an accuracy loss? So we introduce our solution. Our solution is ONNC, which is an AI compiler. And we also cooperate and integrate with Arm CMSIS-NN, which is Arm Cortex-M neural network library. So combining these two powerful tools, we can unleash intelligence power of IoT devices. For our customer, our user, you only need to bring your data, use your familiar tool like PyTorch, like TensorFlow Lite, or even Keras. We can use these input from your familiar framework as our input, and we can compile it and use CMSIS library. We can run it on your devices. And let me introduce these two tools. First, ONNC, which is an open neural network collection. We mainly developed by Skymizer. Is an open source AI compiler. And we support various neural network frameworks like PyTorch, like TensorFlow, and even TVM. And also, it's also a tool chain we support. We provide compiler, calibrator, and even runtime. So in Cortex-M, it's a fully utilized, it's a very compact solution for IoT devices, for AI models. And also, thanks to Arm's CMSIS-NN, which provides a very powerful neural network library for Cortex-M devices. And it provides many neural network functions for various devices. Okay, then let me introduce our technology. You may wonder why we can optimize memory usage without accuracy drop. That's because Skymizer is an AI compiler company. We focus on compiler technology since 2013, and we leverage many compiler technology from latest 40 years. We use like legalization, we use technology in calibration, we use scheduling technologies, we use many compiler technology to optimize our memory usage. Let me give you an example. Like we use layer splitting to optimize our memory usage. Like in this unoptimized solution, you may use W1, 2, and 3 in the same time. But because we are compiler, if compiler analyze this graph, we can easily find some part is not dependent, some part of data is not dependent on other parts, which means we can split these layers into like, we can split X1, X2 into X1 and SA, X2 prime and SB. And we can split non-dependency part from dependency part. So we can sacrifice just a little bit time and we can gain the many memory usage optimization, like we can reduce these parts of memory usage. And further, we also can, if for some cases we cannot split the memory, we can also figure out the rearrangement, the weight, and try to optimize its memory usage to make sure it is under the memory usage limit. So that's what we use compiler technology for optimization memory usage. And you may wonder, isn't this only optimized for some AI framework? The answer is not. We support various machine learning framework as our input, like TensorFlow, Keras, and TBN. Why we can do so? Because we leverage MLIR, which is a hybrid IR interface, can as a common language between AI frameworks. So just that many machine learning frameworks use the same grammar. So we just need to replace vocabulary between different AI frameworks. So like this, MLI provides a very simple way to describe operators. So for us, we describe our convolution like this way, domain-specific language to describe our convolution in our ONNX. So when we try to translate operator from other framework like this fully connected in TensorFlow Lite, we just need to write this simple description to describe how to transform fully connected in TensorFlow Lite for Micro to ONNX like GMM and Redo. And because ONNC is natively support ONNX, so we can easily to transform the models from different AI frameworks. So by using MLIR, we could support TensorFlow as our input. We just implement some TensorFlow dialect, and it can easily transform it to our ONNC dialect, and we can generate its output. And also we use the same approach to support TBN as our input. So in next part, we are going to introduce our experiment results. our experiments, we use Arm Cortex-M4, new Maker IoT M487, which has a 196 megahertz CPU and use 512 kilobytes flash memory for storage, and which has 160 kilobytes SRAM, which is for memory. And also we use G++ 6.3.1 cross compiler and embed 5.15 and use 1.3 CMSIS-NN Library. And for benchmark, we use MLPerf Tiny version 0.1 as our benchmark, so which contains visual wake words, which is use MobileNet as its backbone, and keyword spotting, and as our which use DSCNN as its backbone, and the image classification, which use ResNet as our backbone, and anomaly detection, which use deep encoded as our backbone. So you can see we can input not only image, but also audio as our input. Okay, so let's check our results. In memory usage, ONNC is only used 3/5 of TFLM in the base cases. In visual wake words, we only use 3/5 in memory usage compared with TFLM. And keyword spotting, we only use 4/5 in compared with TFLM. That's because we use compiler technology to increase memory locality and also reduce peak memory size simultaneously. So how about code size? In code size, ONNC is only 1/10 of TFLM in the base cases. And in like image clarification, we only use 1/5. In visual wake words, we only use 1/7. In keyword spotting, we only use 1/8. And in the base cases, anomaly detection, we only use 1/10 code size compared with TFLM. That's because ONNC is compile based while TFLM is interpreter based. That means TFLM needs to use interpreter in your IoT device. They need to install an interpreter in your IoT device, but ONNC doesn't need it. So ONNC can have a very advantage in code size. So we talk about our advantage, but how about performance and accuracy? Does we sacrifice our performance? The answer is no. In most of cases, like visual wake words, keyword spotting, and anomaly detection, it's very close to TFLM. There's almost no difference between ONNC and TFLM. Furthermore, in image classification, ONNC even have a better performance. We use less time to execute image classification model. So actually, we are very close in performance. Most of cases, it's close to TFLM. Furthermore, in some cases, we have further performance improvement compared with TFLM. So how about precision? In the very beginning of this talk, we talk about embedded software engineer may need to trade off between precision and memory usage. But in ONNC, with the ONNC's help, embedded software engineer no longer need to trade off between these two. Like this, we compare with our ONNC solution with TFLM and the golden version. And in most cases, its performance difference between these three frameworks only 1 to 3%. So there is only very, very little accuracy sacrifice compared with 5% or even 10%. So this is our ONNC experiment result. You can see we can gain many memory usage improvement without performance sacrifice and without precision accuracy sacrifice. So let's go into the demo part. We'll provide you very slight introduction to our ONNC. First, install ONNC and then create a workspace, get and apply your license key, create, build, and deploy your ONNC project, and then get a compiled model and integrate the compiled AI model into your embedded project. And finally, deploy your embedded project into your development board. And you can get all of this getting started from skymizer.com/tinyONNC. You can check this document in here, this orange button, document orange button here. Okay, first step, install ONNC. Go into your command line, open your command line and use pip to install ONNC bench. And then use pip show ONNC bench to check whether you install successful or not. And then create a workspace and check whether you create is successful or not. Then, because tinyONNC is a SaaS, as software as a service, so you need to register in our website to get your license key to use our SaaS service. So go to shop.skymizer.com and register your account, then apply your 30-day free trial, and then you can get your license key from your mailbox. Apply your license key to access your tinyONNC SaaS service back to your terminal, and then fill the license key by in your ONNC login command. Then you just use create project to create your project, use a build project command to build your project, and use deploy project command to deploy your project. And then just check the compilation results by check the output folder to check your compilation result. You will have one file and one folder. In this file, compile underline report.json file, you can check your RAM usage and your flash usage. In SRC folder, you can find the compiler model, which is C++ file and .h file. And you can use these CPP files and H file into your embedded software project. You only need to use four APIs to integrate your embedded project, right? Input, use your model to inference, and then read output, finally, release allocated memory used by your model. Okay, let's check how to integrate compiled AI model into your embedded project. Here is an example. You may have various input, like input from your camera, your microphone, and when you receive this input, and you may put this input into this input array, and then you write this input into your model, use ONNC underline write underline input, and then use your model to inference this input, and then you will get the output. And you use your output data, receive your output data in output array, and finally release ONNC, release memory space used by ONNC. And finally, how to build your project for your devices. It's highly dependent on your devices. And in following step, we will show how to build and run in NewMaker IoT M487. First, deploy the model by embed for your devices like you use embedded deploy and embedded compile to compile the embedded project mentioned in the step 5. And then put your binary file to your devices. And third, execute a model and check your result. And like this, you can execute your model and check the result. Like this, we use visual wake words, so we can check whether this picture is anyone in this picture. The model say, no, there is no anyone, there's no person in this picture. And so this is our demonstration for our model. And finally, TinyONNC, we're asking for free trial users. You can check on skymizer.com/tinync, and you can get your free license key from shop.skymizer.com. Feel free to contact us for further information. And thank you for your participation.
Thank you, Peter, for your introduction. Welcome to the next partner, Alex Luo, VP of Cyberon's Embedded Solution BU. He's presenting a DNN-based voice trigger and command recognition algorithm on Arm Cortex-M55.
Hi, this is Alex from Cyberon. In my talk, I will introduce our new generation DNN-based voice recognition algorithm for MCU platform called DSparter, including its recognition performance and how it reduces the development cost, and with Arm's Helium technology, the performance enhancement on Cortex-M55. Today, I'm very happy to have this opportunity to introduce our new generation DNN-based algorithm called DSparter for voice wake-up and local command recognition, and the results of performance enhancement by Arm Cortex-M55. Let me give you a brief of our company. Cyberon is a professional software algorithm company located in Taiwan and established in year 2000. Cyberon have devoted to speech technology for more than 20 years. Last year, there are more than 30 million devices equipped with our technologies and shipped to worldwide markets. The product includes smart toys, consumer electronics, home appliance, IoT, wearable, and automotive devices. About 80% of our employees are software researchers and engineers. So basically, we are a technology-oriented company. And we are located in Taiwan, but target on global market. For command-based recognition, such as the DSparter I will introduce today. Currently, we support more than 40 languages around the world. This is one of the main competitive advantage we have. We are still developing more languages and have to cooperate with customers and partners to reach the global market rapidly. We provide several kinds of speech solutions for various platforms, and from single keyword detection, continuous speech recognition, to the complicated dialogue system with natural language processing for specific domains. And besides voice recognition, we also provide text-to-speech to support the complete voice interfaces. This page shows our solutions by 2 dimensions. One is the resource requirement, and the other is the technology capacity. The yellow part in the middle is the local dynamic command recognition solution called Cyberon. It's the process 3-layer fixed grammar, and the recognition vocabulary is set at runtime through the API by applications. And it works for present talk voice control and has been applied for name dialing, application launch, and music control on mobile phones for more than 10 years. And following the popularity of mobile internet and cloud computing, we launched a voice search application called VoiceGo in year 2008, and then integrated it with the natural language processing and dialogue technologies. It became a voice assistant service for users to access Taiwan daily life information. And this is a blue part in the upper right corner. Unlike a traditional command-based recognition, users don't have to memorize the verbal commands, just interact with the system by their spoken free speech. So this kind of voice service, such as the Apple Siri, Amazon Alexa, and Google Assistant, let the public have a new understanding to speech technologies and drive the overall population. But sometimes there are certain limitations on network access, perhaps due to the device themselves or the network quality. So we apply the natural language processing technologies on local recognition too, to provide the free speech control on certain limited domain devices. And this is a Skymizer, the green part about the middle. By the way, one of the main features of voice recognition is hands-free. But in above solutions, users still need to press or touch the device to start recognition. This action reduces the convenience of using voice and bring another demand. It's called voice wake up, which is the orange one on the bottom left. Voice wake up needs to work in always on mode. So therefore, usually MCU or DSP with limited resources but low power consumption is used for realize this function. And besides a single wake-up word, it can be extended to multiple keyword recognition as well, and provides voice control interfaces for resource-limited products, such as home appliances, smart toys, IoT devices, and so on. We have a new generation algorithm on this field called DSParter, and I will introduce it in detail in this session. All of these solutions, except the cloud-based solutions, Arm has always been the main platform of our local voice technology in embedded system. For example, the C-Listener and Skymizer solutions are mainly applied on Cortex-A platforms. And regarding the voice trigger and local command recognition, we have previous generation algorithm, DSParter for Cortex-M0. And the new algorithm, DSParter, has been ported onto M3, M4, M7, M33, and today the M55. So following the growth of Arm's hardware performance, we are able to continuously provide our algorithm with higher recognition rate and lower resource consumption. Basically, there are two kinds of voice recognition demands on MCU platform at present. One is the voice trigger or wake-up word recognition. Just like Hey Siri or Alexa, it detects the predefined specific keyword in always-on mode and is followed by further speech recognition. On one hand, it saves the computing resources of the recognition in long-term mode. And on the other hand, it helps to avoid or reduce the misoperation caused by daily conversation or background noises. The other demand is local command recognition, usually performed within a limited period of time. It recognizes multiple fixed commands. Then the system can execute the corresponding action according to the recognized command. It provides an alternative to traditional button or touch interfaces. By this combination, we can achieve the completely hands-free operations. Besides, with the launch of Arm Cortex-M55, we see that the MCU platform provides more and more powerful computing resources. I believe that a natural spoken language interface will be realized on MCU platform in the near future. And this is one of our the task in our roadmap. Okay, so local voice recognition on MCU can bring the following benefits. And first of all, using voice is the most natural and convenient interface. And compared to the cloud-based voice services, it provides quick response and is not affected by the network bandwidth or stability. For device manufacturer, the voice function is completely built into the products. So there is no cost on maintaining the voice service. And for users, their privacy can be better protected. Nowadays, COVID-19 changes people's life and behaviors a lot. People tend to reduce or avoid touching things directly by hands. So voice control helps people to stay safe and healthy. This brings another strong demand of voice recognition on MCU platforms. However, there are some challenges when we want to introduce voice recognition on MCU. First, it's hard to find a qualified algorithm which can run efficiently at low resource platforms, because traditional speech recognition is a complicated algorithm with big acoustic model to have good enough performance. Usually, it's not designed for small platforms. And secondly, to run voice recognition in always-on mode, the power consumption is a big issue, especially for battery devices. And third, if the algorithm is downsized to be able to run on MCU platforms, due to the limitation of resources, the recognition performance may be reduced. It may just work at a certain clean or quiet environments. And this leads to the next challenge. In real life, there is usually flow of various sounds in the background. To resolve this problem, speech preprocessing algorithm like noise reduction or far field recording is needed to reduce the noises. However, speech preprocessing may bring a distortion to speech signal, and this will unfortunately reduce the recognition performance. So developer may have to take efforts on fine-tune both algorithms carefully to ensure the performance, and this may increase the uncertainty to product development. And last, by conventional approach, it needs to collect a lot of training data for creating the customized keyword model for recognition. And usually, the training data are others of hundreds or thousands of people. So it takes tremendous time, money, and human resources, and you may miss the time to market. Therefore, to fulfill the market demands and to overcome above challenges, based on our practical experience and accumulated over the past years, and the latest edge computing AI technologies, we developed a new algorithm called DSPotter. DSPotter is developed for the always-on, always-listening voice trigger and local comment recognition. It could work in always-on mode to detect the wake-up word with high accuracy rate and low false alarm rate. And it also works for multiple commands recognition to achieve local control functions. Next, DSPotter has high noise robustness. It adopts a state-of-the-art DNN-based modeling for well-designed keywords. The accuracy rate can reach over 90% on the SNR 5 dB situations in general, even without speech preprocessing. Of course, speech preprocessing still helps, especially for heavy noisy environments. DSPotter has a wider tolerance range for audio quality. So this time it's much easier to reach the match point of both preprocessing and recognition algorithms. So developer can save a lot of time of fine-tuning. And that's how to create the recognition command efficiently. We use the phoneme-based approach. Phoneme means the basic element of a language, and every language has its own phoneme set. For each language that this part supports, we, Cyberon, collect a large amount of training data from native speakers and build a best course model in phoneme level on our server side in advance. So we provide a tool for developers to create the recognition commands by text input. So developers just have the text of the command, check and confirm the phoneme labels. Then they can get the recognition model for the customized commands almost immediately. So by this way, it's no need to collect the huge amount of training data in advance. Okay. And this Sparta's architecture separates the engine code and model data. So it can switch the recognition command set easily and quickly, even without changing the code. And this will minimize the effort of change commands for different applications or scenarios, especially for products that support multiple languages. And this Sparta engine itself is language independent. And the language dependent part is a course model of recognition commands. So we provide a friendly tool for developers to create their customized command easily. Just select the language he wants and then input the text of the command. This tool will predict the pronunciation from the input text and generate the customized keyword model by pre-trained phoneme model of the language. Okay. Again, it's no need to collect the training data in advance. This tool heavily reduces the effort of the developer of developing voice recognition products and help customers to meet the time to market as well as meet the global market. This page shows the available language that this Sparta supports. There are more than 40 languages that present covering most major languages over the world, and including some localization versions for regional accents, such as English, beside the US English, UK English, and Australian English. This Sparta also supports Chinese accent English, as well as the Singaporean, Filipino, Indian, and Southeast Asia accent English. And we are developing new language continuously. So by our roadmap, there will be 2 new languages done by the end of this year. Here are references of this Sparta's recognition performance. On the left-hand side, the test is on a single trigger word, in Chinese, 赛为你好. And when we test it at clean environment, the accuracy rate is almost 100%. Then we add background noise with several levels to the testing data. You can see if not SNR is 10 dB, it still keeps a very high accuracy rate and drop a little to around 90% at SNR 5 dB. But at 0 dB, that means the noise level is the same as speech. The hit rate is reduced to about 50%. For this case, you should consider to adopt a preprocessing algorithm. If the SNR can be enhanced by 5 dB, the recognition rate will be improved a lot. And the blue line is the performance of a smaller model. Its performance is a little bit lower than the larger model, or the orange line, and in noisy environment. And on the right-hand side, there is another reference of 11 commands, including 2-syllable to 6-syllable keywords. And basically, the performance is almost the same as a single keyword. This page shows the resource requirement of this butter. You can see it's quite low. As I mentioned, this butter engine and command data are separated. So we can control the resource requirement by the model size. And basically, we offer at least 2 models of different size for each language. And the larger one, we call it level 1 model. The base model size is 155 KB, and it needs about 45 KB heap RAM. On Cortex-M platforms, it takes 60 MCPS CPU if without optimization. And for the smaller one, the level 0 model, it takes less data, RAM, and CPU resources than level 1. Of course, as shown in previous page, the recognition performance is a little bit less than the level 1 model in noisy environment. Another feature of this butter is that only few additional resources are needed when the number of commands increase. Take a keyword of 4-syllable as an example. The additional data size is just 32 bytes, not 32K, 32 bytes. And the RAM is 128 bytes. So on many Cortex-M4 chipsets, this butter can support more than 100 commands. To overcome the challenges I mentioned above, besides the algorithm itself, hardware performance, hardware platform plays an important role as well. We are very happy to see that Arm launched the Arm V8.1M architecture with Helium technology. For example, inside this butter, the vector dot product operation takes a very high portion of the total computation. Cortex-M55 provides a 128-bit SIMD and MBE instructions, which reduce the dot product computation significantly. By the native code, you can see it takes about 656 cycles each time. And then if we optimize with the SIMD instruction on Cortex-M4 platform, the cycle count is reduced to 249. And we use the MVE CMSIS API on M55. It's further reduced to 110. And finally, optimized by assembly of MVE. The cycle count is just only 97. So for this part, we can get the computation performance enhanced by 6.76 times with MVE instruction on Cortex-M55. And the total computation of this butter is reduced to 20 MCPS from 60 MCPS. And this means that we can save more power or have more resources to provide data recognition performance. The common model of this butter are created by a PC tool called this butter modeling tool, or DSMT. We provide this tool to the partners and customers who have signed the algorithm license agreement. And developer can create their customized keyword model just by text input. Again, there's no need to collect training data in advance. Then we can verify the recognition performance by streaming audio input or by pre-recorded web files. And according to the test results, we can optimize the performance by adjusting the model parameters on this tool. Next, let me take a few minutes to demonstrate how the tool works. This is a PC tool for creating this sparter model. It's called this sparter modeling tool. Let me create a new project, give the project name, and select the language we want. You can see the available languages in this list. Let me pick Worldwide English. And confirm some settings in the folder for this project. Okay, next, what we have to do is just to input the text of the commands. Suppose I have a product for mobile phone accessory, and I'd like to support both iPhones, Siri, and Android phones for Google Assistant. So I just need to tap the trigger word, like Hey Siri, and OK Google. Okay, you can see the system this tool will predict the pronunciation of each command. This is Hey Siri, and it found two possible pronunciation of OK Google. One is OK Google, the other one is OK Google. And you can decide to keep this pronunciation or remove it if it's not necessary. So then we can save the project, and the customer command is created immediately. It's just so easy. Okay. We can verify the customized command and dispatcher by the online test tool and offline test tool of the SMT. The online test tool takes the streaming audio input to test the dispatcher and the customized commands. You can see my waveform, the waveform of my speech here. And if I say, Hey Siri, it will show the detect keyword here with the time information and the confidence score and related information. Let me try again. Hey Siri, Hey Siri, OK Google, OK Google, OK Google. As I mentioned above, each sparter has high noise robustness. So let me play some noise in the background. See background some double noise. And I say again, Hey Siri, Hey Siri, OK Google, OK Google. You can see this sparter and the customized command model still work well, even without any tuning. It's very easy to create a demo or prototype. And for mass product, we suggest the developer can collect some testing data from the target device and do the offline test. The offline test will take a pre-recorded web file to do the recognition simulation. Besides a single web file, we also can give a script file containing multiple web files and recognition reference. So with this information, it will do the recognition on the web file one by one and calculate the recognition result, the hit rate, and false rejection rate, and false rejection rate and the false alarm, number of false alarms. Okay. And by this tool, we also provide the simulation of noise environment. You can select the type of noise and set the noise level. For example, let's just apply the SNR 5 dB double noise on the testing data and do the simulation again. So this time in the SNR 5 dB environment, the accuracy rate is 90%. So according to the recognition result, developers can further optimize the performance by the adjusting the parameters here and optimize the recognition performance. Here are some application references of this pattern, including in the field of automotive, wearable, and hearable devices, and smart toy, media player, home appliance, smart home devices, smart speaker, etc. And now Arm Cortex-M55 provides plenty of computing resources. So we are looking forward to more possibility by the cooperation with you on Cortex-M55 and bring more convenience by voice to everyone. And once again, I'm very happy to have this opportunity to co-work with Arm and to introduce our voice recognition algorithm, the D-Spotter here. And thank you very much for your attention. I hope you enjoy it and look forward to the cooperation with you in the near future.
Thank you, Alex, for your sharing. The final speech will be delivered by Young-Yong Boon, CTO and co-founder of Edge Impulse. He's going to share with us, enable your IoT ARM devices to hear by giving them a new brand.
Hi, I'm Jan, and in the next 30 minutes, we're going to show you how you can give your IoT devices eyes, ears, and actually a completely new brain using embedded machine learning. So my name is Jan Jungboom, and I'm the co-founder and CTO of Edge Impulse. We're a startup focusing on bringing embedded machine learning to a wide variety of devices all around us. And the reason why it's so cool to be here at the Arm Endpoint AI Computing Summit is because me and Arm go a really, really long way back. Not only were the first devices that I actually shipped Arm devices, that is not a big surprise. There are billions and billions and billions of devices shipping every year with Arm tech in it. But I actually worked at Arm for 3.5 years out of the Cambridge office. And in there, I worked on a wide variety of products, including Mbed, Pelion, but also some kind of novel stuff around embedded machine learning, including microtensor, which grew out of Taiwan. So Neil Tan was the initial developer of that, working at the Arm Taiwan office. And a whole bunch of other random stuff that you can still see to this day on the Mbed Labs page. Kind of anything from simulating microcontrollers to running higher level languages on these types of devices with JavaScript on Mbed. So really, really kind of fun to be back here on the Nest. I visited Taiwan for the Arm Dev Summit, or whatever it was called, a couple of years ago. I remember eating very good xiaolong bao. So kind of sad that I can't be there in person, but this is the next big thing, next best thing. And to be here. If you want to reach me, you can do that at jan@edgeimpulse.com. So if we're thinking about IoT devices and kind of the applications that people build with these types of devices, kind of the very first 101 that everyone starts building is a temperature sensor. And a temperature measuring IoT device is easy because if I want to know what is the temperature outside, the only thing I need to do is go on DigiKey and buy a thermistor or a digital thermometer. Like this is an analog thermistor, just 3 pins, power, ground, and then an analog voltage signal. Then I read that out, I get the current temperature, and I send it to the cloud. And this gives me information from the real world, but in kind of a limited fashion, because this approach, and this is something we see for lots and lots of IoT devices today, of the only thing that we actually capture is stuff where we can just buy a sensor off the shelf and then read that data and send it out, severely limits kind of what we can do with our devices. It limits it to exactly the thing that off-the-shelf sensors can measure, and this is, I think, why we have lots of temperature sensors, IoT temperature sensors, which is why we have lots of parking sensors, because you can just measure the magnetic field of a car going over it or leaving, and stuff like push buttons, because, well, it's just a single signal. And while that indeed gives us a little bit of insight into the real world, it's really temperature data from the real world, it severely limits kind of the applications that we can have here. there's a lot of other stuff that is really hard to capture, but I think it's much more interesting. For example, on the savannah, do I hear an elephant? Yes or no? And send that to a central location. This is very interesting because now all of a sudden I can use kind of the standard senses that we have, listening or seeing or even feeling vibration, to detect stuff in the physical world. Now naturally this is much harder for the very simple reason that I cannot go to DigiKey or Arrow and say, oh, I want a elephant detection sensor. Impossible. That's kind of unfortunate because for me, this is where the really interesting part is. Just think of the infinite number of sounds and images and motion all around us. You know, everything that you currently perceive while you're watching this talk, like everything that you hear, everything that you see, everything that you feel. And think about all the kind of conclusions that you might want to draw from that. Someone is walking by, I hear glass breaking or hear something that requires my attention. That is stuff that is interesting to me, not just yet another temperature sensor. But so far it's been really hard to utilize that type of data because we can't, because on one end the bandwidth of this is really high. Just think about like how much audio you can generate on a typical microphone. It's like 16,000 samples a second. Try writing a control loop to control that. And it's very complex, right? If I have a cold chain monitoring system, it's very easy to say, okay, well, if temperature is above 20 degrees, then something is amiss. Whereas I need to write a control loop that I can actually detect when I hear an elephant trumpeting, much harder because of this infinite number of sounds all around us. And even if we have the compute or we have the algorithms in a central location, maybe somewhere in the cloud, it's often not feasible to just send raw data, for example, raw audio data, to the central location because our devices are cost constrained. We can't slap a radio on everything. They're power constrained. We have probably have a battery that we need to run off for a longer period of time. So sending raw data doesn't work really there. And we might have a bandwidth constraint here as well. Not every device actually has the bandwidth to send raw sensor data over. So how can we fix that? And I think this is where machine learning comes in. So the really hard part is kind of this infinite sounds and images and motions all around us, right? We know that if I listen to a sound of an elephant trumpeting, I know, because of my experience as a human, that was an elephant. But writing that control loop on your embedded device where you say, well, I have these 16,000 values, 1 second of audio. Now I need to write some rules, my normal control loop, to then detect elephant or no elephant. That is really hard. So machine learning is a different way of writing your application. So rather than taking your input, your sensor data, and your rules, and then you as a programmer create those rules and then you have an outcome, we swap those things around. And in machine learning, we say, well, if we know that between sensor data and an outcome is a correlation, but it's really hard for a human to write that, we can have a machine learning algorithm that helps there. So rather, we say, well, we have our sensor data, we know what the outcome should be, elephant trumpeting, help me find those rules. So I like to think of machine learning not as a magic black box or something. It's in essence, it's just a different way of writing your application. Rather than you providing the rules and then checking if the outcome is correct, now you provide the input and the outcome, and the rules is something that the computer can figure out. So this is really widely applicable. So these are some of the use cases we see today. I think there's a lot more really cool stuff coming in the future. Naturally, stuff like recognizing sounds, great. Biosignal analysis. If you have a wearable, the chances are pretty big that there's a machine learning algorithm actually determining what activity you're doing, or what your sleep phase is during the night. Classifying images, even really hard to do in a control loop as well. Relatively straightforward with a machine learning algorithm. And even stuff like detecting abnormal vibrations and anything in between. Kind of everything where you have messy, high-resolution sensor data, perfect fit for machine learning. Now, you might think, okay, well, Jan, yeah, cool, machine learning, I've quite a lot about it, but for me, machine learning is this. It's a data center full of GPUs churning away. What does that have to do with IoT? So I think it has everything to do with the fact that it's not magic. In the end, it's just a different way of writing your application. And that also means that if you design your machine learning algorithm, if you design kind of the constraints within it where that machine learning algorithm is to work in a way that will actually make it run on device in the same way as you would write your control loop normally. So let's give you an example of how that actually works and how an ML model is just an algorithm, and algorithms can run on any type of hardware. So let's say that I'm writing a control loop, a normal application, to detect whether water is boiling. Very straightforward. So I have a temperature sensor, and then whenever the temperature is above 100 degrees, water is boiling, otherwise water is not boiling. That is pretty straightforward. So I write that control loop, I write that algorithm, and then I get the temperature up to 102 degrees Celsius. According to my algorithm, the water should be boiling, and I observe that that is indeed the case. It's great. I lower the temperature to 98 degrees. According to my algorithm, it should not be boiling. I observe it's not boiling. Okay, great. Q&A passed. Shipped firmware. So, but now we add an additional variable. So we go mountain climbing, and we're at 2 kilometers high. So according to my algorithm, water should not be boiling, right? It's under 100 degrees. But then I observe that it actually is. So something has changed. Yeah. Back to the Q&A drawing table. So here we know that there's a correlation between the temperature, the altitude, and whether the water is boiling. And rather than trying to write this out ourselves, we can ask a machine learning algorithm to help us here. So our first step is that we start collecting data. So we have the temperature at 98 degrees, 102 degrees, and the altitude, and what we observe, so the outcome. So this is what we call our data, and this is what we call our label. So what a machine learning algorithm then can do is find a mathematical function that most accurately maps the data to the right label. And because the machine learning algorithm has no idea about what temperature or altitude or even water is, that takes lots of trial and error. It doesn't have any inherent information about the data that it's looking at. But after all this trial and error, it will just find a mathematical formula. That might very well be this one, And there's no difference, literally no difference, between you as a programmer writing that formula or the machine learning algorithm finding it. And once you think about that, hopefully that kind of snaps straight away in. It doesn't matter if you write the code or the machine learning algorithm writes the code. It is just math underneath. And computers are incredibly good at math. A typical Cortex-M4 microcontroller can do 40 million operations a second already on this stuff. So if the only thing we want to do is kind of run the inference, run the control loop after finding this mathematical formula, that is something we can totally do on an embedded system. And you, as the programmer, still have influence over that by controlling the number of parameters and kind of the shape of this mathematical formula early on. Then again, if you want to retrain, you say, hey, well, some of my observations were incorrect. Okay, cool. Let's still do that in a data center. But just by running kind of the outcome, the mathematical formula that our ML model finds, that is already incredibly useful on our devices. So let's take a look at, going from zero to a model, like an actual real use case. So let's say that I have a factory, and in my factory there's a restricted area, and no humans should be there. So I hang up a couple of microphones. So everything starts with raw data. So the stuff that I might want to collect is, well, footsteps. So that is an indication that a human is somewhere. I want some machine noise. So, what is the normal sound that machines make? And maybe some other stuff that indicates that humans are there, like conversations. And we can always say that you want to try and get this data at the highest resolution possible. We can always downsample at a later point. The next step is that we want to extract some meaningful features from that. So the raw audio, that is a lot of data, but it's also very noisy. And this can be really kind of notoriously hard to deal with and be really messy. So what we typically do is, or what we do for lots and lots of data is that we say, well, on-device intelligence is not a new thing. We've been doing signal processing, for the last 40 years. Let's first see how far we can go with that. Let's clean up the data with signal processing. Let's remove kind of the frequencies that we don't think are going to be useful. Let's add some noise floor to remove some of the noise. So, for example, we can generate some spectrograms. So these are MFE spectrograms for footsteps, the machine noise, and the conversation. Once we have that, and this is a lot smaller resolution data. So here we have a picture, but it's a lot less data points than the 16,000 that we had in the raw waveform, and it's a lot more clear, right? I can kind of look at this and identify that the first one is probably footsteps based on that. Then we can let the computers figure it out, and that's where the machine learning stuff comes in. So first we need to determine what question are we actually asking. So do we want to know what is happening right now? Classification problem. Do we want to know if the current behavior is out of the ordinary? Anomaly detection. Or do we want to know what is going to happen in the future? Forecasting or regression. And part of this is also saying, okay, what are the constraints, where do I need to run it in? So this mathematical formula that we try to find, you as the developer are still in control over how many parameters, how big can this formula be? And then the computer figures it out. And then finally, we deploy. So what we've done with Edge Impulse is kind of build this complete end-to-end pipeline, where the final part of what we do is just exporting all the algorithms that and the formulas that you found as source code, highly optimized. So this is actual on-device performance characteristics running on a Cortex-M4 of doing footstep and conversation detection on the factory floor. So the signal processing step, in this case, takes about 200 milliseconds for a second worth of audio data. And then the classification part, so after I've extracted those features, what is then happening, takes about 30 milliseconds. So we heavily leverage hardware acceleration, vector extensions, etc., to make this run fast on device. So a really cool part, a unique part of our IP that we actually have, that I think is going to be incredibly useful for anyone shipping devices and trying to lower the BOM, is the Eon compiler. So this comes as part of Edge Impulse, and it's a neural network compiler for general purpose MCU that spits out source code for those mathematical formulas. And that yields, if you've ever done something with TensorFlow Lite for microcontrollers, this yields significantly smaller models. So we typically see about a 35 to 50% decrease in RAM usage and a similar number in flash usage. And that can often be the difference between using a smaller version of the same MCU and thus actually saving money. So yeah, to get started with all of that, you might think, wait, this is really cool, Jan. Like, how do I as a developer get started and utilize this in my toolbox to build solutions? Well, that is why we put together Edge Impulse. So Edge Impulse is the place to build embedded machine learning models. It's from engineers, for engineers. We're 30 amazing people that know everything about signal processing, data collection, building IoT devices. And really kind of help you every step of the way. So from this initial data collection, to verifying that the data that you have is actually good, to signal processing, to extracting some interesting information from that with machine learning, all the way to deployment. And we have an amazing community that to date has created over 37,000 real ML projects. So it's really amazing. And free for developers. So everything that I'm going to show you in a demo in a little bit, you can just go to edgeimpulse.com and start building. So awesome. We're basically compatible with every ARM device on the market. So if you have any dev boards, whether it's an MCU device or a Linux-based device, just go look at the data forwarder docs. It's really easy to get that data from your device. And then you can deploy it to any device that has a C++ compiler. So that includes every Cortex-M0 all the way to a Cortex-A or even to stuff with a GPU like the Jetson Nano. But the idea is that we try to build, models that are the smallest possible and always try to help you find something within the constraints of your device. If you don't have any hardware on you, you can use your phone. I'll actually do that in a demo to show some stuff. So with that, I want to switch over to the demo part, and let's actually see what it entails to build a real ML model from scratch. So this is an Edge Impulse project, and from here you acquire new training data, you design your impulse, which is kind of what we call our combination of signal processing together with a machine learning block, and we finally train and validate that model. So everything starts with data, and if we think about a keyword spotting model, so something where I say a phrase like, hey Siri, okay Google, or in this case, hello world, I want the device to respond. So first I need examples of just that, hello world. If you have a phone, I have it actually connected here already. You can do that straight from here. So my phone is connected to Edge Impulse. You can just scan a QR code, go to the website, and that's all we need. And I say, well, I want to collect some hello world data. So let's try that. Hello world. Hello world. So that gives me, well, in this case, 2 samples. Now this is a 5-second sample, and I'd like to keep everything to a second, because that's kind of how long my keywords are for a uniform data set. So here I say split sample, and we'll automatically find the 2 occurrences of where I actually set something. So hello world and hello world. I click split, and this is how I build up my data set. Now we've done that together with a bunch of colleagues already, and in total we've collected a little bit over 8.5 minutes of hello world data. And then, as I said, we also need some other data that's not hello world, because the machine learning algorithm, the stuff that needs to find this formula, has no idea about what a keyword or what hello world is. So we need to give examples of other stuff too. So here we have unknown, so other words, maybe yes, no, other people speaking, and we have background noise, so any type of normal noise that you might hear in a system. So those are the 3 things we have. From there we go to our impulse design. And an impulse kind of starts with normalizing data. So here we're going to look at a 1-second window. Then we're going to have a feature extraction pipeline. In this case, we'll use an audio block that extracts a spectrogram from this data. We have a wide number of types of spectrograms already in here, plus a way of actually plugging in your own if you want. Here we use MFVC, which is actually tuned specifically for speech. And it filters out lots of other frequencies that have nothing to do with speech, which is a great choice for this type of solution. And then we'll have a classifier. And here we're actually going to determine which of those 3 things we actually heard, whether it was hello world, noise, or unknown. Those are the 3 outputs. So our spectrogram, here we have our raw data on top, and this is the spectrogram that comes out. As said, at every point we'll actually show you what the on-device performance is going to be. So here we have 236 milliseconds per inference on an M4. If I play around with my parameters, let's say I want to use some less filters, now it's only 185. But my spectrogram changed a little bit. So toying around and finding those parameters has a direct effect on on-device performance. And we have a way of automating this and kind of finding this stuff automatically. I'll show that in a little bit. So some stuff that we then do is that we show you the quality of your data set after the signal processing step. So here every sample in your data set is color coded, and we see nice separation. We see blue here, which is hello world all around. We'll have orange, which is noise, and then we have unknown words, which are in green. But relatively nice separation. And this is here we can easily find kind of data samples that might be incorrectly labeled. So let's look at blue dots in the sea of orange. And that's probably data that is mislabeled. So let's take a look at this. So this is a blue dot in the noise cluster. And this is indeed HTML ruffling with a bunch of papers. So this is a way for us to kind of identify mislabeled samples and filtering them out easily. Click view sample, delete it, and go from there. From there, we can train our classifier. We have a wide variety of type of models, from typical classifiers to regression models to anomaly detection, etc. Here we just want to know which of these 3 things it is. The mathematical formula that we try to find, the number of parameters, that is determined by the neural network architecture. So we'll try to load one that's going to work for the type of data you're looking at, but you have full freedom here visually, or if you have a data scientist at house, you can say switch to expert mode and you just get code. But we train the model, good accuracy, but especially here, if you look at the hello world class, so 96.5% accuracy on that specific class. And for noise and unknown, it doesn't really matter too much. If some unknown data is classified as noise, I don't care. The only thing I'm really interested in is about the hello world thing. Once again, we also show kind of what is mislabeled data, interesting stuff like hello world, what are the hello world samples that were misclassified, and we're finding the exact sample that we had earlier, the one that we identified as this is probably not good. So this is definitely one that we need to remove from our data set. But that all looks good. We have a nice working model. So to deploy that back to device, you just go to deployment, click C++ library, and build it, and then you just get a C++ library out. Just source code. Full source code, Apache 2 license, no royalties. Includes our SDK with all kinds of signal processing blocks. One little side note, so if you think, hey, finding those parameters, like should I use 32 filters or 40 filters in my signal processing block, or what is a good architecture of my machine learning algorithm, we are working, and this should be out by the time that this video lands, on the Eon Tuner. It's a way of actually finding the best working or the best machine learning model that will run on device. So you give your constraints. In this case, it needs to run on a Cortex-M4 at 40 megahertz. You give your target latency and the amount of RAM and ROM that your target has available, and will automatically go through every potential combination of signal processing and ML pipeline and give you the model that works best within the constraints of your device. So you see the parameters here, number of filters, etc. are away. So trying to find it automatically, that is something that our tooling can do as well. The Eon Tuner. So once you've exported this as a C++ library, the people at Microchip have been awesome enough to already create a example project in MP Lab. So the only thing you need to do here is just call run classifier continuous. I see it as a driver, but instead of just getting raw sensor data, you now get a conclusion out. And then you just integrate it into your application as usual. Here we print some debug information. But the key part here is that if we see hello world with at least 70% confidence, then we print heard keyword hello world. But naturally you can send a message over MQTT or drive a sensor, etc. easily from there. So you build in Flash as usual. I've done it already for time's sake, but let's take a look. Model is running here, no problem. Hello world. Hello world. Cool, and that runs actually really fast. So we take about 200 milliseconds per slice. Lots of extra time left here to do other stuff on your main loop. So really easy to build this and integrate that and really try and see what your devices can do. All right, I hope that you have a good understanding of the type of problems that machine learning can solve. Naturally, I think the really interesting part here will happen the moment that people will start utilizing machine learning for stuff that you never thought of. So here's a really cool example of Benjamin Cabet from Microsoft who built an artificial nose, and that is running on a Cortex-M4 from Seed Studios, Wio Terminal. So he actually made the cover of Make magazine with his artificial nose. Really, really cool, right? For me, naturally, images and classifying that is straightforward, or at least I can pretty easily imagine, you know, what is happening and how I can utilize that in a product. Same with audio, maybe even vibration. But look at all the other different sensor types. So this is actually using sensor fusion over a gas sensor and some other environmental sensors to start classifying these type of different things. So really, really cool. If you want to read about it, so this is the May volume of Make magazine. It's like 25 pages on TinyML, Edge Impulse, build instructions and all that kind of stuff. So if you have the opportunity to pick up a digital copy, they're still available from the Make magazine website. Really, really cool. And if this kind of stuff in general is super interesting for you, you want to learn more, then come to Edge Impulse Imagine. It's an online event as well. You can, as part of it is in person, but you can follow everything online. It's 3 days of amazing talks by industry leaders from companies like Google, Microsoft, Aura, and Edge Impulse naturally, combined with fantastic workshops by our community, our wide variety of silicon vendors, and even a peek into the future of what we can do with Arm, for example, an M55 and Ethos-U55 silicon. So that you can find on edgeimpulse.com/imagine, and I hope to see everyone there naturally. So with that, I want to do a small recap of what we've learned over the last 30 minutes. First, I hope that after you've heard me talk, but also seen me actually put something together, you know that the machine learning hype is real. Machine learning is here, and it can really solve problems, and it can help you build better products already today. I think that is super awesome, really, really interesting. The second is that machine learning and sensors are an absolute perfect fit. The typical bandwidth of a modern sensor, like even a MEMS accelerometer, allows you to capture data up to like 1,000 hertz. And right now, we just throw most of that data away. We look at the data and we're like, well, okay, let's take the average motion over the whole day or over the last hour, and that's what I send over. But there's so much more interesting information that we can capture from that. And machine learning is the way of turning that messy, high-resolution sensor data into actionable results. So really, truly perfect fit. And yeah, and in essence, like, we're not building stuff in a vacuum. Let's take a look at all the data that our customers, that the people that we build their devices for, currently collect. And let's see how we can take advantage of kind of all the sensor data that we currently throw away. And start building some really, really innovative IoT solutions going into the next year. So with that, I want to thank you once again, invite you to Imagine. If you have any questions, head to our forums or just drop us an email at hello@edgeimpulse.com. And we can't wait to see what you'll build.
As we are approaching the end of our event today, I'd like to invite Arm FAE Director David Hsu again to wrap up for this.
Thank you all for participating in the whole event today, and I hope everyone can get a lot. With AI ML, the future world is full of imagination. Smart devices will be everywhere, making human life more convenient and safer. Let us work together to spark the world's potential. Looking forward to seeing you next time.
I'd like to appreciate all the participants being here. We hope these brilliant speeches not only help you get a better understanding about the development trend of AI technologies, but also help you develop endpoint and edge AI devices more easily and efficiently. Thanks again for joining us today. We will see you next time.